Hello everyone, welcome back to TechSimplifiedTV. I'm Munmun and today's VLSI Physical Design Marathon is your complete walkthrough of the back-end chip design flow. We will start with partitioning, that is, breaking down a big design into few manageable blocks. Then we will move to floor planning to decide how these manageable blocks are placed to get best usage of area and power. Next comes pin assignment and power ground routing that ensures strong connectivity and most efficient usage of power connection. After that, we will dive into placement followed by global and detailed routing. This way, we will lead to a situation where all the signals are effectively connected. Finally, we will wrap with specialized routing by understanding clock network, clock tree synthesis, clock routing, and different techniques of clock network routing. By the end, you will clearly see how a design transforms into a chip, combining material, physical, and design perspectives of modern VLSI design. So if you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and partitioning. Next, more on partitioning, level of partitioning. After that, why partitioning is important. Next, rules of partitioning, graph theory and partitioning, pin and net-oriented netlist, partitioning algorithm. There is another slide on same topic, that is partitioning algorithm. So these are the pointers we will cover in today's episode. We are done with this slide. We will move to the next slide. Design flow and partitioning. This is the VLSI design flow that starts from system specification, then architectural design, functional and logic design, circuit design, and here front end ends. Now physical design, that is basically back end, and physical design is not a single step. There are multiple steps like partitioning, chip planning, placement, clock tree synthesis, signal routing, timing closure. Once everything is done satisfactorily, then that moves to physical verification and sign off, and after that fabrication and packaging and testing, and finally the physical chip come to customer's hand. So VLSI design cycle is broadly categorized into front end and back end. We know that front end starts with system specification and if it defines the logical behavior according to the functional specification. At the end of the front end, we get technology mapped gate level netlist. So this is the objective of front end. Now backend starts from there, and main focus of backend is to translate the circuit we have got in front end into silicon wafer with proper placement of blocks, essential power lines, routing, and etc. After all these steps, the process lead to tape out. So this is a small description of the flow. Now partitioning is initial step in physical design process. Partitioning is dividing a chip into smaller blocks. As the name suggests, now different functional blocks are separated and routing placement is simplified. The designer breaks the larger design into various smaller functional modules or blocks and then proceeds with implementation of these smaller modules during RTL design phase. These smaller functional blocks are structurally linked in the main module. Main module is called top level module. This type of partitioning is called as logical partitioning. So there is a top level module and there are some other modules also. The total design, a bigger and complex design that is divided into smaller blocks and they are handled separately. That is the main theme and purpose of partitioning. We are done with this slide. We will move to the next slide. So more on partitioning. To simplify complex integrated circuit design, they are divided into smaller parts called modules. These modules can be simple as few electrical components or as complex as fully functional integrated circuit. If the total design is doing multiple work and very complex work, when we subdivide the total circuit into smaller parts, so one part is as good as a functional IC. A tool called partitioner splits the circuit into smaller sub-circuits, partitions or blocks. It aims to reduce the number of connections between these partitions while adhering to design rules like maximum size and delay limits. So Partitioning might help us. Also, we have to consider some other constraints like design rules, allowable maximum size, and delay limits. We cannot ignore them. There is a example circuit with 8 gates, and we can cut it or divide it into 2 different ways. Like this is cut 1. If that is the cut 1 in one section A, B, C, D, these 4 gates in block A, and E, F, G, H, these 4 gates in block B. So we are following same connection, keeping the connection same, that is functionality same. So interconnect between these 2 blocks is 2. Now if we divide the circuit in different way, like A, B, D, E comes in one block and C, F, G, H comes in another block, keeping the same functionality, number of interconnects here become 4. So how we arrange the gates depending on their functionality, interconnection between them, number of interconnections depend on that. Now, if each block is designed without considering the others, it can lead to problems. Since both the blocks are part of a big design, so we have to consider others also while designing one. More connections between partitions can increase circuit delay and decrease reliability. We know interconnection, reliability issues related interconnections are there. Airdrop will be more. So too many connections can create dependencies that slow down the design process. The main objective is to minimize connections between subcircuits to improve performance and meet design constraints. That is the main objective. So constraint may include limit on logic size in a partition or number of external connections that is limited by the number of I/O pins on a chip. Now, by following these points, designer aim to create efficient, reliable, and easily manageable integrated circuits. A designer has to follow all these constraints. So we are done with this slide. We will move to the next slide. Next is level of partitioning. Now, circuit partitioning is an important task in VLSI design application. Partitioning algorithms are used to achieve various objectives such as circuit layout, circuit packaging, and circuit simulation. Partitioning can happen at 3 levels: system level, board level, and chip level. There is an infographic. At system level, if we do partitioning, we lead to some PCBs, multiple PCBs. On a single PCB, if we do board level partitioning, we lead to some multiple chips. And at chip level, if we do partitioning, we end up with subcircuit or block. So, system level partitioning, a system is partitioned into group of PCBs. Each subsystem can be designed as single PCB. Board level partitioning, a PCB is partitioned into subcircuit. Each subcircuit fabricated as VLSI chips. And third, chip level partitioning, circuit assigned to chip is divided into manageable subcircuits. So this is all about level of partitioning. Now we are done with this slide. We will move to the next slide. Why partitioning is important? This is the main theme of partitioning. This is the system now break into multiple modules. Physical packaging. Partitioning decomposes the system in order to satisfy the physical packaging constraint. The partitioning conforms to a physical hierarchy ranging from cabinets, cases, boards, chips to modular blocks. Divide and conquer strategy. Partitioning helps manage complex designs by breaking them into smaller parts. This approach allows team members to work on different sections, creates a logical order for design, converts the netlist into a physical layout for planning, assigns cells to specific areas for placement and RLC extraction, and coordinates between logic and layout for simulation. So divide and conquer strategy, a big complex system, divide and different team member can work on different sections. So that actually is the process. Now system emulation and rapid prototyping. On one way to test a system is by using FPGA to create the hardware. Now since FPGA often have less space than modern VLSI design, this prototype system use several FPGA arranged in hierarchy. A partitioning tool is needed to fit the netlist onto the hardware. By partitioning, we are reducing the whole system into smaller parts, and FPGA often have less space, so hierarchically we can use FPGAs, arrange them and fit the netlist into those. Partitioning tool can contribute here. It is needed to fit the netlist into the hardware. Now hardware and software co-design. For hardware and software co-design, partitioning is used to decompose the design into hardware and software. Management of design reuse. For huge designs, especially system on chip, we have to manage design reuse. Partitioning can identify clusters of netlist and construct functional modules out of the cluster. Part of a design can be reused. That actually saves time and money. In that case also, partitioning helps. This block diagram we have already used in our previous slide. Here also we have used it just to show how partitioning breaks a bigger module into smaller modules. So we are done with this slide. We will move to the next slide. Now, rules of partition. We can do partitioning, but there should be a constraint. There are some rules we have to follow. There are some points we need to take care, like interconnections between partitioning. Reducing interconnection decreases delay and interaction between partitions, simplifying independent design and fabrication. So, interconnection between partitioning, we have to keep that is less, because more interconnects means more delay and more reliability issues. Partitioning a circuit may result in the critical path crossing between partitions multiple times. That might increase the delay. Number of terminals. The number of net needed to connect a subcircuit to other subcircuit does not exceed the subcircuit's terminal count. That's a constraint. Now, number of partitions. A large number of partitions can simplify the design of individual sections, but it may also increase fabrication cost and the number of interconnections between partitions. Another thing is area of each partition. There is a spelling mistake. There should be 1A, area of each partition. Area of each partition is also a very crucial point, because the whole area of core is determined by the floor planning. Floor planning give you the total area. Within that, we have to fit all the partitions, and how those partitions are arranged, how those blocks are arranged. That is another part of floor planning. But the constraint is there. Total area constraint is there. Delay constraint is there. How many interconnect, that constraint is also there. So area is another point, because power performance area constraint is always there. That factor we cannot ignore. So these are the rules we have to follow. And there is a diagram. So there is one PCB, there is another PCB, PCB1 and PCB2. There are two chips where there are two modules, A, B, and another chip, that is, there is a module C. So this A module of this chip 1 is communicating with B. That time is X. When it's communicating within same PCB another chip, time increases 10x. If it's communicating with D, C to D, that is 20x. Now, if we bring that module within that chip where C is there in another design, so overall that communication time between C and D reduces. So how we place the module depending on their connectivity, depending on their connections and function, how frequently they need to communicate with each other. We have to keep it all in mind. So that way partitioning can be done. It's not that randomly we do it. No, obviously not. Depending on the functioning and depending on interconnections, and because longer interconnection means a lot of time is there required. So we have to take care all of these things. Now, what happens after circuit partitioning, or what we get after circuit partitioning? Area occupied by each partition is estimated. Now, possible shapes of blocks can be ascertained. Number of terminals required by each block, that is also known, and netlist specifying connections between block is available. So these things we have, and from there we will move to floor planning. So we are done with this slide. We will move to the next slide. Now, graph theory and partitioning. Graph theory is the core thing behind partitioning. Whenever we are taking example of smaller circuit with 7-8 gates. Now think, when number of gates thousands or in millions, how will we, with the complex connectivity and complex functioning, how will we do that? That's a real tough thing to do. So there comes utility of mathematical models. That is behind all the commercial tools, popular tools. They use those mathematical models behind them and do it. There comes the importance of computation. Now, graph theory is the basic of partitioning. So graphs are used in physical design algorithm to describe and represent layout topologies. A graph is G, function of V and E, is made up of two sets, elements and edges. Set of nodes or vertices denoted as V, and relations between elements denoted as E. So this is a simple graph. These are vertices. and their connections edges. So elements and edges. Now this is hypergraph. A hypergraph consists of nodes and hyperedges. So these are nodes and these are hyperedges. In a graph, an edge is connected with two node or two vertices. In case of hypergraph, multiple node can be connected. In a hypergraph, edges are set of any number of vertices, not restricted to number 2. Hyperedges are commonly used to represent multi-pin nets or multi-point connections within circuits. So basically, in practical, our circuits are also multi-pin and multi-point connections. So hyperedge is suitable to represent them. Here we can see there is one hyperedge E2 consisting these two nodes 1 and 2, E1, 1 and 3, E4 is with 1, 2, 3 and 5, and E3 is with 2, 3, 4. These are hyperedges. So this is graph, this is hypergraph. Now there is a circuit, simple circuit with 7 gates, and if we represent that circuit with the graph, that is this way and hypergraph this way. Now notice this point, how it's different. C, E and G. E and G both are connected to C. So if we represent with graph, because in graph two nodes can be connected, C to E is connected and E to G is connected this way. And hypergraph, multiple nodes can be connected. So C to E and G this way connected. This is the difference between graph and hypergraph. So order of hypergraph, size of vertex set, and size of hypergraph, size of the edges set. This is the definition of order and size of hypergraph. So we are done with this slide. This is very basic of graph theory, and with a small circuit, a very small circuit, we just try to represent how it can be represented for understanding only. Now we will move to our next slide. Now pin and net oriented netlist. Everything we are doing, we actually do this partitioning on netlist. So a netlist is a list that shows all the connections on nets and the components they link together in a design. It can be organized in two ways, pin oriented and net oriented. This is the circuit, this is net oriented description, this is pin oriented description. Netlists are created during logic synthesis and are a key input to physical design. We already have a series on synthesis and EOSIS. Watch it for better understanding. Now a connectivity graph is representation of netlist as a graph. Cells, blocks and pads corresponds to nodes while their connections correspond to edges. So we have presented it as a graph also. So in net 1, net 2, net 3, net 4, net 5, their descriptions. From this description we can understand the circuit. This is gate X. Net 1 is connected with input 1 and Y input 1. Net 2 is connected with input 2 of X and input 2 of Y. This way, description is done. Now, a net 3 is connected with X, output of X and input 1 of Z. This way, connection is done. So, this is the graphical representation of this circuit. So, this way, pin and netlist can be represented in pin and net oriented way, and we can represent it in graph also. So, now we are done with this slide. We will move to the next slide. Partitioning algorithms. A cell is any logical or functional unit built from components. A partition or block is grouped collection of components or cells. The components are there and a group collection of components and cells that makes a partition or a block. The K-way partitioning problem seeks to divide a circuit into K-partition. The most common partitioning objective is to minimize the number or total weight of cut edges while balancing the sizes of the partitions. Often partition area is limited due to packing considerations and other boundary conditions implied by system hierarchy, chip size or floor plan restrictions. Because of that, now circuit partitioning is very hard to solve. As the problem gets bigger, the time needed to find the best solution grows very quickly. There is no known fast and perfect method to solve balance constraint partitioning. There are two types of partitioning methods, constructive and iterative method. A constructive algorithm creates a partitioning from graph that represents the circuit or system. Iterative method work to improve the quality of an already existing partition or solution. And deterministic or probabilistic method, deterministic program always produce the same solution each time they run. Probabilistic method give different solution each time because they use random numbers. So these are the types of partitioning. And these required methodologies are all within the tools. There is a small example. There is one block, another block. There are 4 nodes, and if we consider the interconnections between them, so there are 9 interconnections between these 2 blocks. And if we rearrange, keeping the functionality same, the connection become 1. So from cut size 9 to cut size 1, that is reducing. We are done with this slide. We will move to the next slide. Partitioning algorithm. This is the second slide on the topic. Now, there are methods which are followed, like methods like Cunning and Lean or KL algorithm and fiducium matrices or FM algorithm can find good solutions and run relatively quickly. Optimization using simulated annealing can address particularly challenging partitioning problems. KL algorithm is sensitive to the number of nodes and edges. KL algorithm performs partitioning through iterative improvement steps. It's based on exchanging or swapping pairs of nodes, each node from a different partition. FM algorithm is sensitive to number of nodes and nets hyperedges. The FM algorithm is typically applied to large circuit netlist. The algorithm is more naturally applicable to partitions of unequal size or presence of initially fixed cells. FM algorithm offers best trade-off between solution quality and runtime. Now, partition area is limited by packing considerations and other boundary conditions such as chip size, floor plan restrictions. We have repeated this point because we have to always remember whatever may be the algorithm or methodology, we have to be restricted by some constraint like chip size, floor plan, etc. And we have to work within that, keeping cost as low as possible, because everything is for business and high cost is not viable for business. Now, let's see what commercial tool contributes here. Now, commercial tool uses command line options or GUI to create manage partitions. So, using usually command line, most of the commercial tools, either they have command line options or they run on GUI. Changes the netlist tree structure to create hierarchy nodes at the top level that can be physically divided. This ensures that the nodes are evenly sized and reduces the number of top level connections needed for hierarchy blocks. So whatever needed, tools does that. They have that algorithm inside them, finds the best way to divide design into blocks that can be worked on separately, makes sure the partitions are balanced by size or number of instances, reduce the number of top-level connections between block I/O ports, ensure the netlist is partitioned without changing how it works. We are understanding all these things with small example, and R&D engineers in commercial tool vendor companies, they are putting all these tough algorithms inside the programming. It requires a lot of human effort, human time. That's why commercial tools are so expensive, does so complicated work. We are trying to understand it, although we don't have to do it by hand, because billions of gates can only be handled by computation. There is no other ways. So we are done with this slide and we are done with our today's episode. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and flow planning. After that, goals for flow planning, optimization in flow planning, flow plan tree, constraint graph pair, flow plan sizing. There are 2 slides on this topic. Next, linear ordering. There are 3 slides on this topic. Then cluster group, and finally simulated annealing. So these are the pointers we will cover in today's episode. Now let's move to the next slide. First, design flow and flow planning. This is an infographic with steps for VLSI design flow, starting with system specification, then architectural design, functional design, then logic design, and then circuit design. Once we get technology mapped synthesized netlist, after that physical design or backend starts. And the first step is partitioning. We have already discussed it in our previous episode. After that comes chip planning. Chip planning, there are 3 steps in chip planning. First is flow planning, then pin assignment, and power and ground routing. In today's episode, we will concentrating on flow planning. After that, placement, clock tree synthesis, signal routing, timing closure, all of these steps are required. Once these are done, then only we move to physical verification and sign off. If any result shows any kind of unwanted thing, we will again get back to that step, repeat it, correct it, and again proceed. VLSI design flow is an iterative method. Through iterations, we get the better result. And after physical verification, fabrication, packaging and testing, and finally, we get the required chip. So chip planning is organizing large part of a chip. Chip planning has three main stages: flow planning, pin assignment, and power planning. A gate level or RTL netlist can be automatically divided into modules. These modules can also be taken from a hierarchical design. Large chip modules are arranged as blocks or rectangular shapes. Now, floor planning decides positions and shapes of these blocks based on the areas and aspect ratios of the modules such that the chip size is optimized. A gate level netlist can be automatically divided, and there are tools for this operation, can be divided into different modules, and that is part of partitioning. We have already discussed. After that, when we go to floor planning, the floor planning decides the position and shapes of these modules or blocks based on the areas and aspect ratio of the module such that the chip size is optimized. We have to arrange those blocks or modules in such a way that total chip area is optimized. There are three targets: chip size is optimized, interconnection is reduced, and timing is improved. This stage ensures that every chip module is assigned a shape and the location. In flow planning, we ensure that every chip module we got from partitioning that get a position and a shape. This facilitates gate placement, and every pin that has an external connection is assigned a location so that internal and external nets can be routed. Now, pin assignment, the second part of chip planning, that is after flow planning, that is pin assignment. Pin assignment connects outgoing signals to the block pins, and IO placement finds locations for the chip's input and output pairs, usually around the edge of the chip. So pin assignment does this thing. In flow planning, what we do at the core area, and after that pin assignment, internal and external pin, their connection is established. And now after the power planning, since every cell or every device need a ground and power connection, so first power planning, doing the power planning is most important. Let them get connected with the power line and the ground line. And next, the signals is routed. So first routing is power and ground routing. So we are done with this slide. Here we are just discussing the design flow and flow planning as a part of chip planning. Now we will go into detail of different aspect of flow planning. So we are done with this slide. We will move to the next slide. Goals for flow planning. There is another infographic. It's a representative diagram of a chip. This is the core area, and these are hard macro like RAM, ROM, PLL, analog block. Now this is the core power ring, IO, and this is the IO power ring. IO cells are there, corner cell. That is generalized structure of a IC. Now, importance of flow plan. Why flow planning is so important? Because arranging the partition blocks on a chip, once we are done with partitioning, we have some blocks, we have to arrange them in this area. This is the core area. We have to arrange them. We have to utilize this place. Placement of macro. There are multiple macros, how they are placed, so that overall area is optimized and interconnections should not be very long. Otherwise, airdrop will be higher. Specifying the location of IO pads. Once this core area is done, then IO pad, there is space for IO pads, specifying the location and number of power pads. How the modules are spaced, depending on that, how power will be routed. So according to that, the power pads are also positioned, deciding the type of power distribution. These all are decided through flow plan. So floor planning is important. Now the core of chip is made up of one or more top level blocks. These are core is surrounded by a ring of pads. The design of the blocks and the arrangement of blocks and pads can affect the overall chip area and hence cost or yield. How this thing is designed depending on the area, overall chip area is, if it increases, so cost and yield that can be affected by this thing. So floor planning is a very important step. Obviously, floor planning is done not by hand, by commercial tools are there. They does all the thing. A module becomes a rectangular block after it is assigned dimensions or a shape. These blocks can be either hard or soft. The dimension and areas of hard blocks are fixed. For a soft block, area is fixed, but the aspect ratio can be changed. A floor planning usually includes following parameters: like the area of each module, all potential aspect ratios of each module, and the net list of all external connection incident to the module. Depending on that, floor planning is done. So we are done with this slide. We will move to the next slide. So what are the required files for floor plan? There are some files and parameters we need to do floor planning. First is synthesized netlist. A synthesized netlist describes the electrical connection of the circuit. It consists of electrical components and list of connected nodes. A synthesized netlist can be written in Verilog or VHDL. So a netlist is required. At the end of front end, we get a technology mapped synthesized netlist. From there, backend starts. We do the partitioning, and in case of floor planning, also it required. Now, physical or reference library. Physical or reference libraries contains physical information for standard cell, macro cell, and pad cells. These informations are necessary for placement and routing because the modules, they are assembly of cells, macro cell, standard cell, IO cell. Different types of cells are there. So we need their data, technology node, others data. So we need that physical or reference library. Now logic libraries. Logic library contain timing and functionality information of all standard cells used in the design. Timing information of hard macros such as IP, RAM, ROM, etc. also provided here. Timing constraint, design constraint, clock constraint, max Q, max and mean insertion delay, number of clock, domain, clock start point, all this information is required. Power requirement, power and ground nets. Floor planning control parameter, die size estimation, core size, aspect ratio, core height, core width. Die size estimation is required and core size, aspect ratio, core height, core width. These data are required because we need to understand how much area is provided to place the blocks. Accordingly, the floor planning will get done. So these are the required files for floor planning. We are done with this slide. We will move to the next slide. Optimization in floor planning. There are 3 blocks, block A, block B and block C. Now, this is the total area. Now, look how we have arranged. 2 different ways we have arranged it. Horizontally, keeping the total area horizontal and keeping the total area vertical, we have arranged these 3 blocks. So, that can be done. Position is changed. How it is placed, position and there, how it's placed, that is changed to see which one is better for interconnection, for power routing and all. Area and shape of global bounding box. The global bounding box of a floor plan is the smallest rectangle that fits around all floor plan blocks. The area of this bounding box represents the total area of top level floor plan, that is full design and asset circuit performance, yield and manufacturing cost. This is the smallest rectangle that fits around the floor plan blocks. The area of this bounding box represents the total area of top level floor plan, that is full design and asset circuit performance, the full design. The maximum holding all the macros. To minimize the area of global bounding box, we need to find the best location and shapes for each module so they fit closely together. Another goal beside minimizing area is to keep the aspect ratio of the global bounding box close to a target value. We can adjust the shapes of individual modules to achieve these. The area and aspect ratio of the global bounding box are connected and both objectives are often optimized together. So we need to keep the modules close enough so that area of bounding box is optimized. Now total wire length. Long connections between blocks slow down signal propagation. For better performance, connections must be shortened. Shorter connections means less wire capacitance, that is reduced energy dissipation. Minimized wire length reduce power consumption. Shorter wire length improve routability and reduce manufacturing cost. If connections are too long or dense in one area, there may not be enough routing resources. Spreading circuit blocks apart can add routing tracks but increases chip size and costs. To simplify wire length calculation, we can connect all nets to the center of the block. This method, accurate for small and medium blocks, allows quick interconnect evaluation, although it's not very useful for a big design. So wire length, total wire length is another point we need to keep in mind. If the modules are very closely placed, then there might be problem or routability might not be that good. If they are placed quite far, then interconnection length increases, that increase power consumption. So we have to optimize that also. If the connection between blocks longer, then signal propagation gets delayed, slow down. For better performance, connection must be shortened. Shorter connection means less wire capacitance, that is reduced energy. So there are things we have to optimize. We cannot go in one side. There are two things we have to balance. We are done with this slide. We will move to the next slide. Now floor plan tree. A slicing floor plan is created by repeatedly dividing a rectangular area starting with the entire chip into smaller rectangles using horizontal or vertical cuts. These are the methods. This is the total area. If we cut with this line, so this total area is there and this area is there. Again, if we cut here, there we get two rectangular blocks. And if this area we cut like this. So here one zone, another zone. In this zone we can cut using another line. And finally this zone we can cut like this. So it's a slicing. How we slice the total floor plan. It's one of the way of doing floor plan. So it's a binary tree with k leaves and k-1 internal nodes. Each leaf represents a block and each internal node represents a horizontal or vertical cut line. Each internal node has exactly two children. So if line is like that, it's horizontal, and if the line comes like that, it's vertical. Let's try to understand. This is a horizontal line first, and from there A and B. From this vertical cut here, this one is coming one horizontal line, so that comes C, and here from that horizontal cut there is C, one part, and from there another cut, there comes D, and from here originated another vertical E and F. We can arrange it like that. Another is like A and B, and from there horizontal, if we think that this section was first divided, so D comes first, then again another horizontal like here C, and within that comes E and F. Although this E and F have in between there is a vertical cut. So we can arrange this thing, represent this floor plan using these two trees. This is a slicing. Now a non-slicing floor plan cannot be formed by sequence of only vertical or horizontal cut in parent block. Look, there is no any vertical or horizontal cut which divide the whole block into two. There is nothing like that. The smallest example of a non-slicing floor plan without wasted space is the wheel. Like if we go this clockwise, like A, B, C, D, E. Another could be A, B, E, C, D. So it's like a wheel. Now floor plan tree. A floor plan tree represents a hierarchical floor plan. Each leaf node represents a block. Each internal node represents horizontal cut or vertical cut or wheel. There are three options. Order of floor plan tree is number of internal or non-leaf node. So how can we represent it using tree and wheel together? There are both things are here. Like now there is a horizontal cut which divides into two. So in one part comes H and I, and H and I again in between there is a horizontal cut. This is the branch. Done. Now rest of the part is this. The rest of the part is like that. Now this is our total area. That is cut by 2 by this. A and B will come in one side. C, D, E, F, G will come to another side. So A and B, there is a vertical cut. That vertical cut. So and A and B again there is a horizontal cut between them. So A and B. And here just look, it's like similar like this structure. It's a wheel. So C, D, E, F, G is a wheel. So we can represent this floor plan using tree. Now we are done with this slide. We will move to the next slide. Constraint graph pair. A constraint graph pair is a floor plan representation that includes directed graphs showing the relationship between block positions. Two types of graph: the vertical constraint graph, the horizontal constraint graph. A constraint graph consists of edges connecting n+2 weighted nodes, one source node, one sink node. Source node is S, sink node is T, n block nodes V1 to Vn representing blocks M1 to Mn. There are blocks starting from M1 to Mn and their block nodes respectively V1 to Vn. The weight of a block node represents the size of corresponding block. The weight of source and sink node are 0. Now let's see what is vertical constraint graph and what is horizontal constraint graph, that is VCG and HCG. Node weights represent the height of the corresponding blocks. Two nodes Vi and Vj with corresponding blocks Mi and Fj are connected with a directed edge from Vi to Vj if Mi is below Mj. Now this is the floor plan. If we represented it vertical constraint graph, so this is source and here it's sink. So we are starting from source. Let's start from below. Now I to H, directed I I to H. Here, if we go this way, comes A, and if we go this way, we get F. If we go straight vertically, that comes C. A, from A it's B, from B, and if there is T, so B to T. One branch is completed. Now H to F. F, there are two connection again, G and E. So G and E, and both are getting to D. Now from E, from E, it's to T, and from D, T. And again C, T to D to T. So this is vertical constraint graph. And if we represent it in horizontal constraint graph, so HCG's node weights represent the width of the corresponding block. Two nodes, Vi and Vj with corresponding block, Mi and Mj are connected with a directed edge from Vi to Vj if Mi is to the left of Mj. So from here we will go from left to right. And here is if Mi is below to Mj. From below to upward, and here in HCG we will go from left to right. Source is here, S is here, T is here. So if we start, if that is S, so there might be four branches. One is B, one is A, one is H, one is I. So B to D to E, B to D to E to T. Another branch is A to C. From C, there might be two way. One is G, one is F. Look, G and F. G is directly connected to E and then T. So G and E connected, and F and F is directly connected to T, that is sync, and here H and I both are directly connected to T. So this way we can represent by HCG. Now longest path in VCG is the mean vertical extent requires to pack the block, floor plan height, and longest path in HCG is the minimum horizontal extent requires to pack the blocks, that is floor plan width, that is the floor plan height, and that is the floor plan width. This is about constraint graph pair. Now comes sequence pair. A sequence pair is an ordered pair S plus and S minus of block permutations. Together, the two permutation represents a geometric relation between every pair of blocks A and B. And if A appears before B in both S plus and S minus, then A is the left of B. This is the convention. If A appears before B in S plus but not in S minus, then A is above B. So S plus like this, S minus this if block A is left to the. In both cases, A comes before B or left to B, then A is left of block B. And in here, look, S plus, in S plus, A comes before in left of B, whereas in S minus, in this pair, sequence pair, B comes left to A. So block A is above block B. In this way, by sequence pair also we can represent this way. With sign, we can represent floor plan. So these are basically about representation. We are done with this slide. We will move to the next slide. Now floor plan sizing. Floor plan sizing determines the minimum area of a floor plan as well as the associated orientation and dimension of each individual block. From beginning, we were saying that in floor plan, we not only place the modules or blocks, we also decide their shapes, aspect ratio and all, how they are placed. Here in floor plan sizing, we will do that. Algorithm uses the shapes of both individual blocks and top level floor plan. Shape functions and corner points play a major role in determining an optimal floor plan. Shape function and corner points. These two are very important things. So floor plan sizing consists of three major steps. Construct the shape functions of the blocks. Before determining the shape of the top level floor plan, we need to figure out the shapes of each individual block first because of overall shape depend on them. So there are two blocks. One is suppose 5 unit by 3 unit. If we vertically place it, this block A is height is 5, width is 3. And if we place it horizontally, height becomes 3 and width becomes 5. Here, if we place it, this block B 4 by 2, and if we horizontally place it, it's 2 by 4. So if in shape function we present like this, like 5 height, this is height, this is width, and 3. This one. Another is 3 5s. For second block 4 2 and 2 4. This is the way how we determine the shape function. Now shape function for two blocks are shown. The shape function HAW and HBW show the feasible height width combination of the blocks. Now what are the feasible solutions? In next slide we will see we can arrange it in two ways. We can take the vertical approach and we can take the horizontal approach. This is the vertical approach where we place one block, where we place the blocks up down manner, not side by side, not in horizontal manner. Here look, this is block A. This is basically 5 by 3. If we position it like this way vertically, so 5 by 3, and if we again take this option, it's a permutation combination we are doing here. So 5 plus 4, 9, and this with this 2 and this is 3, so maximum will be 9 by 3. This way it can be, if it's vertical and it's horizontal, it will become 5 plus 2, that is 7, and here the width become 4, and here it's 3 within that, so there is some extra space. Here also there is some extra space, and this one is both are positioned in horizontal manner. 3 by 5, 4 by 2, so 3 plus 2, 5, and the maximum 5, and calculate the area. 9 3 is a 27 unit, 7 4 is a 28 unit, and 5 5 is a 25. Obviously this one is a minimum, and here we are, this is the shape function, and here we are positioning 4 plus 5, 9, 5 plus 2, and we are making the final height as a function of width. This way, this is the vertical approach. Now we will see the horizontal approach. So we are done with this slide. We will move to the next slide. So determine the shape function of the top level floor plan. The overall shape of the top floor plan is based on the shapes of the individual blocks. Combining the blocks in either vertical or horizontal way can lead to different outcomes. There we saw as a vertical positioning. Now it's horizontal positioning. Horizontal positioning, that is side by side. It's coming side by side. So here again, like this 3 by 5, and here 4 by 2. So 5 plus 4, 9, and maximum 3. We are now positioning it vertical, like 4 by 2 and 5 by 3, 7 by 4, and 5 by 5. These are the combination. Here also coming that 5 by 5 is the smallest one. Find the floor plan and individual block dimension and location. After figuring out the shape of the top level floor plan, the smallest possible floor plan area is calculated. These minimum area floor plans are always located at the corner points of the shape function. Once the corner point with minimum area is found, we can determine the size and position of each individual block by tracking back from the overall floor plan's shape to each block's shape. This is the position, that is 5 by 5. This is the minimum. Here also we can find that 2 by 4 and 3 by 5. If we position like this, that becomes the minimum. So 5 by 5. This is floor plan sizing. We are done with this slide. We will move to the next slide. Now linear ordering. Linear ordering, there are 3 slides on this topic. That linear ordering algorithms are frequently used to generate initial placement solution for iterative improvement placement technique. The goal of linear ordering is to arrange the given blocks in a single row to minimize the total wear length of the connections between them. We position them in a single row. And now there are some prerequisites. We need to understand few definitions. Based on that, we will arrange the blocks. New net, what is the definition of new net? Have no pins on any block from partially constructed ordering. So how we will understand what is partially constructed ordering? Like if that is the original structure and we can see these are the net connections and we want to minimize it. We want to rearrange the placement of this block such that the net length becomes less, right? So from one point we have to start. So we will go from in one row, as it's mentioned already, from left to right. So one after one we will start doing. One after one we keep on arranging. So it's partially constructed from left to right. Now it's an example, like if there are 3 blocks terminating, which are terminating nets. These are what are new nets? It's starting from here and have no pins on any block from partially constructed ordering. There is no other pins here. Now and continuing net, there is one connection starting from here, one connection, and then going in a other direction. And what is gain? Gain means of any block M is number of terminating nets of M minus new nets of M. So gain of Y is here N1 minus N4. N4 is new net from here and it's terminating. So 1 minus 1, 0. There are 5 blocks A, B, C, D, E and 6 nets. N1, N2, N3, N4, N5, N6. This is the original design. And here N1 is connected with A and B. N2 is connected with A and D. N3, A, C and E. N4 is B and D. N5 is C, D and E. And N6 is D and E. A is our initial block. So let's start. Remember, new net, terminating net and continuing net. There are 3 types of net. So we are done with this slide. We will move to the next slide to understand the linear ordering. This is the original design. So in first iteration, block A is there. New nets are N1, N2 and N3, and terminating net, there is no terminating net. Gain is -3. Next iteration 1 is done. So now next iteration. So we have B, C, D, E. 1 is placed, right? So B, C, D, E. In B, N4 is new net. Terminating net is N1. So gain is 0. C is N5. In case of that, new net is N5. Okay, we do it the same thing, N5. And continuing net, that is N3, this one continuing. So here C has gain -1. In case of D, there are new nets, 3 new nets here, N4, N5 and N6. And terminating net is N2 and continuing, that is terminating net. So here gain is -2, and in E, N5 and N6. N5 and N6. These are new nets, and terminating net is, there is no terminating net. Continuing net is here, that is N3 is continued. So here also -2. In between all these three, highest gain, which one has highest gain? That is B. So after iteration B, we are placing block B after A and re-establishing the connection, that is N1 net is between A and B, and the way it has. So up to this point, there is no change. These two are done. Now C, D, E block are left. So there are 3 blocks left, C, D, E. That is iteration number 2. C, D, E. Similarly, new nets N5 and no terminating net. So gain is -1 in case of D, N5 and N6. And terminating nets are N2 and N4. So gain is D 0. And in case of E, gain comes -2. So in between 3, maximum value is 0. So gain is, highest gain is with D. So we will place block D after that. So there are 3 blocks we have placed. And accordingly, nets are connected. Now we will move to next slide to place 2 more blocks, C and E. This is iteration number 3. C and E left. No new nets, terminating nets and no terminating nets in case of C. So its gain is 0. And in case of E, terminating nets is N6. So 1 gain. And in case of C, so E will be positioned then, and finally C. So once we simplify the net connection, the arrangement will be A, B, D, E, C. This is the arrangement. In this way, we do the linear ordering, keeping mind in new net, terminating net and continuing net. So this is the linear ordering algorithm. This way we arrange. We are done with this slide. We will move to the next slide. Cluster growth. Floor plan is created by adding blocks one by one until are placed. Start by choosing an initial block and placing it in any corner. In corner and growth in that direction. Each new block is added and merged with the cluster either horizontally, vertically or diagonally. The position and orientation of each new block depend on current cluster shape. The goal is to place blocks in a way that best meet floor plan objective. Only the orientation of individual blocks are considered. The order of adding block is determined by linear ordering algorithm. Blocks are added in such a order that overall floor planning are minimum. Obviously, that should be the goal. So first block A, then B is placed like that, and in this area C, there is another block that could be arranged so this way. This is cluster growth. We are done with this slide. We will move to the next slide, that is simulated annealing. Simulated annealing algorithms work by starting with an initial random solution and gradually improving it. In each step, they look at nearby solutions by making small changes to the current one and choose a new solution from this option. Unlike greedy algorithms, simulated annealing algorithms don't always reject solutions that are worse than current one. In a greedy algorithm, if a new solution is better, for example, has a lower cost, it's accepted and replaces the current one. If no better solution is found nearby, algorithm stops and it's stuck at a local minimum. The main problem with greedy algorithm is that they only accept changes that improve the solution. The idea of annealing can be used to solve complex optimization problem. In case of minimizing cost, finding the best solution is like finding the lowest energy state of a material. Simulated annealing algorithm starts with a messy high-cost solution and mimic the annealing process to create a more organized lower-cost solution. The simulated annealing algorithm is random by nature, so running it twice usually gives different results. The difference in outcome comes from random decisions like how new solutions are created, for example, by swapping parts and whether those changes are accepted or rejected. In a greedy algorithm, if it gets a local minima, it will just stop in case of simulated annealing, it doesn't stop. It goes for a global minima. It goes for not for local minima but for global minima, and the results are random. So any two runs doesn't mimic its result. So that is simulated annealing. These kind of algorithms are behind the tools. Tools uses these algorithms to solve the floor planning problem. In this episode, we are talking about the algorithm and mathematical parts of floor planning. What is behind the floor planning, how we do it, what are the algorithms, and how we can represent. So we are done with this slide. And we are done with our today's episode. Hello and welcome to TechSimplifiedTV. In our last episode, we have discussed about different aspects of floor planning. Once the top level floor planning is done, the connection between internal and external pins are assigned. Along with that, power and ground lines are routed. In our today's episode, we will discuss about pin assignment and power ground routing. If you are interested, stay tuned and stay focused till the end of the video. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and pin assignment. Next, more on pin assignment. Third, pin assignment using concentric circles. There are 2 slides on it. Concentric circle method is a method to do pin assignment. Another method is in next slide, that is topological pin assignment. This is another method. There are 2 slides on it. Next, we will move to power and ground routing. So design flow, power and ground routing. Design of a power ground distribution. After that, planar routing. There are 2 slides on it. Mesh routing. There are also 2 slides on this topic. So these are the topics we will cover in today's episode. We are done with this slide. We will move to the first slide. Design flow and pin assignment. This is the infographic we are using from last episode. Floor planning we have already done. Now comes pin assignment. In chip planning, there are 3 steps: floor planning, pin assignment, and power ground routing. In today's episode, we will cover these 2. And first, now we'll concentrate on pin assignment. So design flow and pin assignment. During planning of the layout of large blocks, placement of the connection points, that is terminals, is very important. When we plan larger blocks in the core area, placement of connection points are important, because how the connection points are defined, depending on that, the signal line will get routed. And when within limited space, we have to route so many connection line, we have to optimize its position and pin location so that congestion problem can be controlled. Now, these connection points are I/O pins and usually placed on the edges of the blocks to keep the wiring short. Our target is to keep the wiring short, and connections are these pins. Blocks are connected with I/O pins. I/O pins are the channel to communicate with the outer world. Now, I/O pins, in last episode on floor planning, we have shared a diagram, a representative diagram or infographics we have showed where I/O pads are positions on the outer. If you can remember, the best spots for these pins depend on how the blocks are arranged. Position of the blocks are important. Now, during pin assignment, each signal on net is assigned a specific pin location to improve the overall design. This methodology is followed. The main goals are to make sure the wiring is easy to route and to reduce unwanted electrical effects both inside and outside the block. Next, the objective of external pin assignment is to link each incoming or outgoing signal to a unique I/O pin. After assigning each necessary net to its designated pin, the connections must be optimized to minimize wire length and reduce electrical parasitics such as coupling or signal integrity loss. We all know when there is interconnect or metal wiring, these are the associate issues: coupling, signal integrity loss. So we try to keep the length minimum, and to keep the length minimum so that we don't need to route the signal line or power ground line unnecessarily for longer length, position of block is very important, and pin assignment is important so that it's the starting of the connection from the block to the I/O. So pin assignment is very important part of chip planning. It's a part of planning. Chip planning, in floor planning, we decide where the blocks are situated, how their shapes are, how much area it will cover, what should be the aspect ratio, as we have discussed in last episode. With all these blocks, they are not isolated. They have to communicate with the outer world so that we can send a signal and get a response. That is the standard method. So now pins, how they are connected. Internal pin to the external pin. In pin assignment, we do that. And later on, we will see that each and every device in a chip, each and every device within a block require power and ground. Otherwise, they are not electrically connected. They are isolated. So every component have to get connected electrically. For that, they must get connection to power and ground. So power and ground is the primary connection. How that signal is routed, that two lines are routed, that is also decided in chip planning phase. We are done with this slide. We will move to the next slide. More on pin assignment. Pin assignment is used to connect cell pins that are functionally or electrically equivalent, such as during standard cell placement. Two pins are considered functionally or equivalent if swapping them does not alter the design's logic, and they are electrically equivalent or equipotential if they are connected. In pin assignment, we connect cell pins that are functionally or electrically equivalent. When they are connected, they are equivalent or equipotential when they are connected, and functionally equivalent if swapping these two pins doesn't change any kind of logic. If that doesn't create any kind of alteration in the design's logic, then they are equivalent. The primary goal of internal pin assignment for cells is to minimize congestion and reduce interconnect length between cells. Why we do that? So that the congestion, one signal is crossing, another signal is going, that kind of congestion does not arise, and to reduce interconnect length between cells, we do this. And the pin assignment technique described below are applicable to both chip planning and placement stages. These are the diagrams here. So this is functionally equivalent pins, how metal 2, metal 1, this color are there, colored mention. This is metal 2, this red, and these are metal 1 layer, poly layer, diffusion layer is there, now contact, via. These are electrically equivalent pins. And if this is the original design, this is an electrically equivalent pin, this pin and that pin. That's why they're connected, and this pin and that pin. Here, now if we swap, if we change their position so that, look, this connection, and here we simplify it. How? Now, this is moved to here, so that directly connected to here, like that. And once this connection is shifted here, this is shifted to there, this position, and swapped. So, this is connected to this one. So next it will be like that. Here it's simplified. This connection is much more simplified. It was crossing each other. Now here it's not like that. Similarly, this and these are equivalent, and now these two are equivalent. So if we swap, so this is simplified. No one is crossing another one. There is no crossing of signal lines. They are not crossing. Are not crossing each other. So this way we swap position, simplify the connectivity. We are done with this slide. We will move to the next slide. Pin assignment using concentric circles. This is a methodology. This algorithm connects a block to all its associate pins in other block with minimum cross connections. It operates under assumption that all outer pins have fixed positions. Inner pins are positions based on location of their electrically equivalent outer pin. The algorithm employs two concentric circles. That's why the name is concentric circles method. The inner circle for the pins of the block being considered, and the outer circle for pins of the other blocks. The primary goal is to assign valid pin location on both circles without no net overlap. So if that is the block, inside block, these are the pins and these are the outer pins. So we consider one. First determine the circles. We consider a circle like that. Between these two columns of pins, the maximum possible circle we are drawing here. And another one is another concentric circle we are drawing like that only. So two circles are drawn such a way that all pins that belong to the blocks are outside the inner circle and all external pins are outside the outer circle. So within these two columns of pins, the maximum place we are utilizing. Similarly like that. And now determine the points. For each point, draw, this point is done. Now for each point, draw a line from that point to the center of the circle. This was the original line. We are drawing a line to center. This is the center of the circle. We are drawing a line this way. So that the line connecting this pin position of the pins and the center, there is a line and that crosses the perimeter of the circle. Similarly, we do for the outer circle also. Okay, and then move each outer point to the where line meets the outer circle and move each inner point to where the line meets the inner circle. So there is a point, so we are shifting two sets of pins, their positions. We are shifting like that. So now these pins positions are shifted on the circle perimeters in both cases. This is the second step. We are done with this slide. We will move to the third step on next slide. Third point is determine initial mapping. The initial setup pairs each outer pin with a matching inner pin, like that only. We are mapping this to that. Similarly, like we can do it in one direction only. We are going clockwise, like that, this way. We have pointed like this. Start by choosing any pin and assign it to an inner pin. Then assign the rest of the pins either in clockwise or anti-clockwise direction. Connection this way. Either we are moving from this way to that or this way to that. Now optimizing the mapping. Repeat the process of pairing outer and inner in different ways. Start with the same outer pin but try pairing with different inner points and then pair the rest of the point accordingly. Continue until all possible pairings have been tried. The best pairing is the one that has shortest total distance between the points. In this problem, an example pairing is shown on the right. At left, the best pairing is in the center and final pin assignment are on the right. We can start from any point and can move to keep on connecting. So we will get different set of connections and the best one is which has the shortest. So we are just moving like that and the shortest one we will take, the minimum. And this way from here we are taking this, that is the shortest one. Now we replace again this circle with the block here, the block and their pins. So that connection is like that. Because this point was, we draw it, we just bring it from the pin of the block, inner block. Now we are replacing with the original points. And now this is the best connection. This is one method. This is concentric circle method. So we are done with this method. Now we will see the next method. Topological pin assignment. This algorithm is an improvement to concentric circle pin assignment algorithm. It takes into account external block positions and multi-pin nets. This allowed pin assignment even when external pins are behind other blocks. So there has some benefit over the previous algorithm. So this is the inner circle or this is the inner block. Main component is M and B is the external block. This is the main internal block and this is the external block. A midpoint line LMB is drawn from center of M through the midpoint of B. This is the center of M and this is midpoint of B. We are drawing a straight line like that. Another line we draw, that is this one, in between B and M like that, so that it intersects the LMB. Pins of B are unwrapped and expanded as line L dash at the dividing point D. Further point in the LMB that intersections B. The pins are then projected onto outer circle. So we draw a line L dash like that. And this way, this pin is like that. We project pins of B like that, this way. We are projecting, and from there we are drawing lines to the center of this M like that. We are projecting, first we project these points on this line, these pin positions on this line, and then projecting on the circuits up to this, like this only. We are done with this slide and let's see what we do next in the next slide. So that is in last slide what we see, that is for one block. Now this method allows multiple blocks to be considered simultaneously. There are two blocks A and B. On block A, consider the midpoint lines LMA and LMB. Two lines are there, LMA and LMB. Two lines we are drawing like that only in from midpoint. And if this is the position, the midpoint D1 is formed this way because it is the further point LMA. This is D1. This is the D2 is formed because it's closer point on LMB, and D3 is formed because it is the further point on LMB. This way. D1, D2, D3. This way we are selecting the points and using D1 to D3, the pins are unwrapped. What we would do? We would do unwrapping first from D1 to D2. So if that is D1 and D2. Then these are the pins 1, 2, 3, and these are A1, A2 and A3. Look from D1 to D2, A1, A2, A3. Next D3, this is D3. After that D2 to D3, D3 to D3. So D3 to D3 means these all will come under it. So that is B1, B2, B3, B4, B5, B6, B7, B8. B1, B2, B3, B4, B5, B6, B7, B8. And now after that this comes like D2 to DA. We are done up to this point. Now D2 to D1. So D2 to D1 means these pins. That is A4, A5, A6, A7, A8. A4, A5, A6, A7, A8. This way. They are projected on this inner circle. So this circle, these are projected. So that is topological pin assignment. We are done with this slide. We will move to the next slide. Now we will see power and ground routing. Again, this diagram, this is power and ground routing. So chip planning involves designing the power ground distribution network and positioning supply I/O pads or bumps. Up to 20 to 40% of all metal resources on the chip are used to supply power, VDD and ground nets because these are the most long interconnects. Every cell needs electrical connection. If VDD and ground are not connected, then those cells are isolated. So these are the longest wearing paths. And the power planning process includes iterative steps such as early simulation of major power dissipation components, initial estimation of overall chip power, analysis of total chip power and peak power density, examination of total chip power fluctuation, analysis of inherent and additional fluctuations causing by clock gating, early analysis of power distribution including average, maximum and multi-cycle fluctuation. These are power planning methods and these steps are done early and these are very iterative steps. Iterative steps to get close to the best result. We are done with this slide. We will move to the next slide. So design of a power ground distribution. Every cell needs both VDD and ground connection. They connect each cell in the design to a power source. VDD and ground supply lines are large, cover entire chip and are routed before any signal lines. Core supply lines differ from I/O supply lines, which usually have higher voltage. Single core power line and core ground line are usually enough, although for some ICs like mixed signal or low power design, we may have multiple power and ground lines. Low power design we have discussed about in our power management series that in low power design, sometimes we use multiple powers for multiple segments of the chip just to optimize the power. Not all portion of the chip requires same kind of power. So for that multiple power supply system is used. This is referring to that only. Routing power and ground lines is different from routing signal lines. Power ground lines require their own metal layers to avoid taking up space needed for signal routing. Now, thicker metal layers, typically top 2 in the manufacturing process, are preferred for power and ground lines due to their lower resistance. They run for the longer length. To keep resistance low, thicker metal layers are used. When power ground networks spans multiple layers, sufficient vias must be used to carry current and prevent reliability issues like electromigration. Supply lines carry high current, so they are often much wider than signal line. The width of each wire segment can be adjusted based on expected current, that is calculated based on current. Wider segments have lower resistance, which reduce voltage drop. There are two main approaches to designing power ground distribution. One is planar approach and another one is mesh approach. The planar approach is used in analog or custom blocks and mesh approach more common in digital ICs. So these are two methods, planar approach and mesh approach. And this is basically about the power lines, why they are wider. Thicker metal layers are used. If power ground network spans multiple layers, sufficient vias must be used to carry current and prevent reliability issues like electromigration. Electromigration may happen because it's heavy current flows. Electromigration is a common reliability issue. We have discussed it multiple times. Sufficient vias must use to avoid electromigration situation. We are done with this slide. We will move to the next slide. Planar routing. The power supply nets can be routed using planar routing when only two supply nets are present in the design. A cell needs a connection to both supply nets. A Hamiltonian path is created that connects all the cells. What is Hamiltonian path? You will see that. The path divides the layout in two regions, one for each supply net. That's a path. It's such that in one side of this path is VDD, another side is ground. Look, it's connecting all the blocks in such a way that on right side VDD and on left side it's ground. Each supply net is routed either the left or right side of the path for each cell. So both supply nets can be laid out without conflicts across the design. Routing the power and ground nets in the planar fashion can be accomplished with following three steps. Planarize the topology of nets. Since both power and ground nets must be routed on the same layer, the design should be divided using a Hamiltonian path. Start routing the power and ground nets from the left and right side, respectively. Ensure both nets expanded in tree-like structure, avoiding overlap and maintaining separation by Hamiltonian path. The precise routing will depend on the pin location. This way, Hamiltonian path is dividing the whole design into two sides. One VDD, here ground. They are connected to each block, although in between Hamiltonian path is going. So this way connection is going on each side. We are done with this slide. We will move to the next slide. Now, layer assignment. Net segments are allocated to specific routing layers considering factors such as routability, the resistance and capacitance characteristic of each available layer, and design rule constraint. How much current will go through that layer, that calculations and everything like resistance, capacitance, all values are calculated and depending on the layers are assigned. Determining the width of the net segment. The width of each segment is based on maximum current it needs to carry. This width is determined by summing up currents from all connected cells according to KCL. For large currents, designers often increase the width by stacking multiple layers vertically connected by vias. Deciding right width is usually an iterative process because currents are influenced by timing and noise, which are in turn affected by voltage drops, creating a cyclic dependency. This loop is typically resolved through multiple iterations and expertise of experienced designers. After completing these steps, the power ground segments are adjusted to avoid obstacles during general signal routing. This is iterative method, and for large current, designers often increase the width by stacking the multiple layers vertically and connected by vias. This way they design it. What should be the right width? That is an iterative process because currents are influenced by timing and noise. Noise is there, timing limitation is there. In turn, that affect voltage drop, creating a cyclic dependence. And experienced designers solve these kind of issues. We are done with this slide. Now we will move to the next slide. Mesh routing. This is another method. Power ground routing in state-of-art ICs has mesh topology. These are 5 steps followed to create the topology, creating a ring. A ring is placed around the main part of the chip and sometimes around certain sections. Its role is to connect the power supply and electrostatic discharge protection to the chip's power network. To reduce resistance, this connection and ring are spread over several metal layers. For example, ring might use metal layers from metal 2 to metal 8 but skip metal 1. This is power rail. This is ring, pad, base, all connections, and this is the closer view. Connecting IO pads to the ring. The image shows how IO pads are connected to the ring. Each IO pad has several metal layers with many small extension, fingers-like structure. These extensions should be connected to the power ring as much as possible to lower resistance and improve the flow of the current to the core. Now, creating mesh. A power mesh consists of stripes placed at set distances across 2 or more layers. The width and spacing of these stripes are based on the expected power, use, and design rule. The stripes alternate in pairs like VDD ground, and so on. The upper and thicker layers are mainly used for power mesh, while the lower layers have fewer stripes to avoid blocking signal path. Stripes on nearby layers are connected with many vias to resistance. How this mesh structure is done, that is described in these steps. So first is create a ring, then connect IO pads to the ring, and then creating a mesh. After that, creating metal 1 rails. The metal 1 layer is where the power ground network connects to the logic gates of the design. Metal 1 to metal 4 connection is showing here. Metal 1 VDD rail, ground rail, then this is a via metal 2, here via metal 2, again via metal 3, now metal 4 mesh. From 4 mesh started. So the width and spacing of metal one rails which determine how much current can be supplied are usually set by standard cell library. The standard cell rows are placed back to back, allowing the power supply to be shared between two neighboring cells rows. This back to back connection is done for ease of connectivity. Now connecting the metal one rail to mesh. Lastly, metal one rails are connected to the power mesh using stacked vias. These stacked vias, it's important to choose the right size of the via stack, that is number of vias in it. Ideally, most resistive part of the power distribution should be the metal one segment between the via stacks, not the stack themselves. The via stack is also designed to maintain flexibility in routing. And from metal 2 to metal stack, metal 4 connection like that, metal 4 via 4, metal 5 via 5, metal 6 this way, and then metal 8, 6 to 8. This way connection, metal layers and then vias, metal layers and vias, these way connections are developed. So this is mesh routing. We are done with this slide and we are done with our today's topic, where we have covered pin assignment and power and ground routing. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and placement. Next, objective and challenges of placement. After that, different types of placement. Next, optimization in placement. There are 2 slides on this topic. Next, global placement. After that, min cut placement. There are 2 slides on the topic. Next, analytic placements. There are also 2 slides on this topic. Next, simulated annealing. More 2 slides. Modern placement, 2 slides. Legalization, 2 slides. And finally, detailed placement. There are also 2 slides. So these are the topics we will discuss in today's episode. There are 3 types of placement. First step is global placement. Next come legalization, and third is detailed placement. We will discuss all in this episode. So let's move to the first slide. Design flow and placement. This is the flow diagram we are using for last few episodes. It starts with system specification, architectural design, functional design and logic design, circuit design, and next when it's entering physical design, there are few steps in physical design like partitioning, chip planning. We are already done with that. Floor planning, then placement. Today we will concentrate on placement, and there are 3 types of placement like global placement, legalization, and third is detailed placement. And once this physical design is done, that verification and sign off is done, then fabrication, packaging and testing, and chip is ready for commercial usage. Today we will concentrate on placement. In the VLSI design flow, placement is a crucial step in the physical design. It comes after partitioning and floor planning. Floor planning and partitioning we have already discussed. Now it's placement. Logic synthesis converts a high level RTL design into a netlist of gates and cells. Partitioning divides the larger design into smaller modules, that is for convenience of designing. Now floor planning allocates general areas for major components and define regions for standard cell, macros. Pin assignment allocates input output, that is IO pins. Once synthesis is done, high level RTL design is converted into a netlist of gates and cells, and that is divided into larger design areas, that is done in partitioning. Then floor planning is allocating those different areas for different types of components, and pin assignment is connecting pins from all those modules to output. After logic synthesis, these are the steps followed, and then come placement. Placement is the process of determining the optimal location for standard cells, macros and other modules within chip's layout. It aims to achieve the best balance between performance, power and area (PPA) while minimizing wear length, congestion and delays. Congestion is also not expected, and wear length, if it's really very long, then heat generate will be higher and delay will be higher. We have to minimize. Optimization is the key. Optimization in terms of PPA, that is performance, power and area. 2 placement phases within PD. One is global placement, another one is detailed placement. So global placement provides a rough layout of the cells and modules to minimize wear length and congestion, focuses on overall optimization but allows overlaps between cells. Detailed placement adjusts the position to remove overlap and ensure cells are aligned with legal sites or predefined rows on the chip. Minimizes wear length deviations introduced during legalization. In legalization, that overlap is removed. After placement, the routing phase connects all components with metal wires, finalizing the design's physical layout. So now we are doing placement. After that, routing is the step. So we are done with this slide. We will move to the next slide.
objective and challenges of placement. Placement is a critical step that transforms a logical design into a physically realizable layout. It ensures that layout is timing efficient, power optimized and routable, forming a bridge between logic synthesis and routing in the IC design flow. So what we are getting from synthesis is a netlist comprised of different cells and gates. Placement should be such that area is minimized, congestion should not be there, delay is minimized, and modules are placed in such a way that connections, power lines are routable. So placement constraints and objective. What are those? Minimize wire length, shorter wire reduce signal delays and improve performance. Timing closure. Placement must ensure path meet the required timing. If very longer path, it will take longer time to reach a destination point. The signal will reach later, so timing cannot be maintained. Power optimization. Efficient placement help reduce dynamic and leakage power. Leakage power more means loss and heat generation is more. That's not good for health of the chip. And congestion control. Placement must prevent routing congestion to ensure the design is routable. So challenges in placements: handling large netlist, efficiency, placing millions of cells. These are the placement challenges. Prevent overlaps. Global placement often creates dense clusters that need to be legalized. That means need to be legalized means there is no overlap. So timing, handling large netlist, one challenge. Preventing overlap is one. Another one, timing versus wear length trade-offs. Minimizing wear length can sometimes degrade timing performance and vice versa. Macro handling large block or macros need special consideration to avoid placement gaps and routing blockages. So these are the challenge we face during placement. These are some diagrams. If that is one module, this one is another, and this is connection between all of them. That is total wear length. Now number of nets. If these are the point representation of nodes and they are connected, so these are the number of nets. Where congestion is represented by this diagram. Congestion means required number of nets are more than that is allowable in the design. That is congestion. This shows signal delay, signal traveling through gates. So from reaching from this point to that point, it creates delay. Optimization is the key facing these challenges. So we are done with this slide. We will move to the next slide. So this diagram is showing different types of placement. If that is the circuit in 2D placement, this could be the scenario. If we place these all gates in linear placement, that is in one row, that is the scenario. And if a better with placement and routing with standard cells, so power line, VDD line, ground line are there. From there, all ground line is reaching all the cells, and power line is reaching all the cells. Power and signal line is reaching all the cells, and this power and the ground line are reaching all the cells, and power lines and signal lines also reaching all the cells. That is much more realistic. So different types of placement and routing with standard cells. How does it look? Cells are positioned here along on outer side. All the power lines are provided and connections are drawn from there. So this is different types of placement. We'll move to the next slide. Now optimization in placement. This is the first slide. Optimization is the key to a good placement. In placement, the optimization objective focus on achieving high performance, low power consumption and manufacturability. High performance, we obviously want high performance. At the same time, power consumption must be less, and manufacturability, whatever we do, that should be manufacturable. So wear length minimization, overlap minimization, timing optimization, roll length equality, congestion minimization, these are the key points. Wear length minimization, what is objective? Reduce the total wear length to lower signal propagation delay, power consumption, routing congestion. More wear mean more heat loss. Power is converted into heat, so power consumption is more and that power is not getting used. It's basically loss. Routing congestion, more wear length is more, so it will create a congestion. Impact: reducing wear length improves timing, that is faster circuit, and reduces the likelihood of routing congestion. Second is overlap minimization, because in global placement, the first step, they are approximately placed, not accurately placed. That is done during legalization. The second step, more refinement in placement. placement, in placing those modules. If the modules are not properly placed, then overlap may happen. So objective ensure no two cells overlap after placement, especially during detailed placement phase. In detailed placement, even if there is an overlap in global placement, we have to correct it during legalization and detailed placement. Impact no overlapping placement improves routability and allows legalization alignment with power rail. Timing optimization objective minimize signal delays by reducing interconnect delays that affect the overall clock cycle. Timing optimization is also get done. Impact enhances the performance of circuit by ensuring faster data propagation through critical paths. Row length equality. Objective is ensure equal row lengths during standard cell placement to avoid inefficient use of layout space. Impact uniform rows prevent area wastage and ensure even wear distribution, reducing routing congestion. So congestion minimization objective is avoid high density areas where wearing overlaps and routing resources become constrained. And approach is spreading cells, congestion aware placement. In congestion minimization, our objective is to avoid high density areas where wearing overlaps or routing resources become constrained. And that could be achieved by spreading cells. Cells are distributed more evenly by scaling their positions and moving them out of dense region. That could be one. Another one is congestion aware placement. Similar to density estimation, routing congestion is estimated on a grid to guide placement. A grid is used to guide the placement, a grid. And impact is reducing congestion ensures routability and avoid post-routing failure. We are done with this slide and we will move to the next slide. Optimization in placement. This is the second slide. Now, power optimization. Objective is minimize the power consumed by interconnects and switching activities. This is more important, even more important in nowadays kind of devices we are using. They are basically mobile devices and dependent on battery power. So if power is limited within a battery, you are giving charge to a battery, so power is limited and expense is more. Obviously, it's a loss. So power optimization is that's why so crucial. Minimize the power consumed by interconnects and switching activities. What is the approach to do it? Reduce wire length to lower dynamic power caused by signal switching across long nets and place high activity cells closer to minimize interconnect delay and energy consumption. There are two approaches. Impacts so leads to low power design which are essential for battery powered devices. We already have discussed a lot about in our power optimization series about this low power design. You can refer to that. Dynamic power, static power, how we can achieve better power optimization. We have discussed there extensively. You can refer to that series. Next, legalization. Legalization, what is objective? Align cells to discrete rows and ensure legal location after global placement. Approach, snap cell coordinates to grid points that correspond to power rails and optimize wire length and overlap during incremental legalization. Impact produces valid placements that meet manufacturing requirements without overlap or misplaced cells. We have to align cells in discrete rows so that there is no overlapping and power connection can be easier. That is the motivation behind legalization. Temperature-based optimization, that is annealing. We will discuss annealing more extensively in later slides. So temperature-based optimization is use simulated annealing to explore various placements and escape local minima in the optimization process. Impact aims for a global optimum solution by balancing interconnect minimization and overlap reduction as the temperature decreases. So that is aims for global optimum solution by balancing interconnect minimization and overlap reduction as the temperature decreases. So this objective collectively ensures that chip layout achieve high performance, efficient power usage, low congestion and manufacturability. Different algorithms may emphasize some objectives over other based on design constraint and priorities. We will discuss some algorithms of placement in later slides. So these are the 8 points we have discussed based on optimization. So these are the factors we consider while do optimization during placement. So we are done with this slide and we will move to the next slide. Next topic is modern placement. Modern placement in EDA refers to advanced method which combines mathematical optimization, multi-objective considerations and sophisticated algorithms to address the demands of current chip design, balancing efficiency, scalability, performance while considering design constraint including wear length, timing, power and congestions. Job is quite complicated because billions of gates are there. We need everything. We need low power, high performance, low leakage, high speed, everything at the same time. So optimization is the key, and to do it manually it's not possible. So we will take help of tools, and tools are guided by algorithms, and algorithms are developed based on physics and maths. So sophisticated algorithm, mathematical optimization, multi-objective considerations, and sophisticated algorithm to address the demands of current chip designs, balancing efficiency, scalability, and performance while considering design constraints like wear length, timing, power, and congestion. So that's quite a critical and complex job. Key aspect of modern placement, multi-objective optimization. Modern placement aims to optimize multiple goals at once, like shortening wear length, saving power, managing heat, improving timing, and easing routing. This approach is key for high-performance, power-efficient chip design. Analytic and force-directed method. Analytic methods are there. These use mathematical models like quadratic and nonlinear optimization to approximate interconnect lengths and solve placement as an optimization problem. Quadratic methods are popular due to their computational efficiency, while nonlinear methods provide better accuracy for designs with various component sizes. Force-directed methods. Here, cells are treated as objects subject to attractive and repulsive forces. Attraction represents connectivity by closely connected cells to move closer, and repulsion prevents overlapping by spreading cells apart. So these are the methods. Hierarchy and clustering techniques. To handle large-scale designs, modern placement algorithms use clustering, which groups highly interconnected cells together in early stages. This reduces the complexity of initial placement and allows for more efficient optimization. After clustering, cells are progressively unclustered and refined in stages, allowing for scalable placement even with millions of components. So hierarchy and clustering techniques in modern placement. First, it groups highly interconnected cells into a cluster, then uncluster them, refining stage by stage. That could be done and in a system where millions of components are there. So legalization and detailed placement. Legalization ensures that cells are moved to exact non-overlapping legal positions, typically aligning with a grid while minimizing disturbance to the global placement. Detailed placement then fine-tunes cell position to reduce minor overlaps and improve wear length and timing by making small adjustments. So in global placement, we place modules, and in global placement there could be overlapping of multiple modules. In legalization, we move those modules so that they are moved to exact non-overlapping positions, typically aligning with a grid, although that positioning must not disturb the global placement. And in detailed placement, fine-tuning of cell position to reduce minor overlapping is done and improve wear length and timing by making small adjustments. So in 3 steps, the total placement is done. We are done with this slide. We will move to the next slide on modern placement. Congestion and density control. Modern algorithms actively manage cell density to prevent high congestion areas, which can cause routing issues and affect timing. Density estimation methods divide the layout in bins and track the area usage in each bin to guide cell spreading. Next is congestion and density control. So modern algorithms, what it does, it's actively manage cell density to prevent high congestion area, which can cause routing issues and affect timing. If the area is very congested, so routing could be an issue there. It's not very easy to a congested area. So density estimation methods divide layout into bins and tracks the area usage in each bin to guide cell spreading. Now timing driven placement. Timing driven placement emphasizes the timing requirement of the circuit. Algorithms assign timing critical paths higher priority, placing these components closer together to minimize delays. Now, machine learning and heuristic improvement. Increasingly, machine learning techniques are integrated into modern placement tools to improve performance, guide decision making, and predict congestion. Heuristic like simulated annealing are also used to avoid local minima and achieve a more globally optimized solutions. These are the main way, and types of modern placement algorithms are quadratic and nonlinear placement, partitioning-based placement, force-directed methods, and machine learning assisted. Quadratic and nonlinear placement approximate wear length as quadratic function and it's computationally efficient, while nonlinear methods are more precise but computationally intensive. So there is pros and cons. In quadratic, it's approximate wear length as quadratic function, it's computationally efficient, whereas nonlinear method are more precise although computationally very intensive or exhaustive. And partitioning based, that is min cut, we will discuss later, divides the layout into smaller section, minimizing inter-region connections. And force directed constructed methods apply attractive and repulsive forces based on connectivity and cell density. Machine learning assisted uses predictive models to improve accuracy in cell placement and routing. Advantages and challenges of modern placement. Modern placement methods achieve higher performance and quality, can handle extremely large designs, and effectively meet multi-objective criteria like power, timing, and congestion control. And challenges: modern placement is computationally intensive, requiring sophisticated algorithm to balance many competing objectives. So many things are there: timing, heat, performance, speed. So many factors are there. So handling all those objectives in a same design is very computationally extensive. The complexity and design constraints of modern chips also demand a high level of optimization to meet performance target. That we know. The demand is gradually increasing with time. So we are done with this slide. We will move to the next slide. Now min cut placement. Min cut placement is a method in chip design where a circuit's layout is divided or partitioned repeatedly into smaller regions to minimize the number of connections or cuts between these regions. The aim is to balance the number of components in each region while reducing the connection that cross boundaries, which helps minimize wear length and improves timing. Min cut placement effectively balances components and reduces interconnections, laying a foundation for efficient routing and timing optimization in later stages. These are the steps. Partitioning. The design area is repeatedly split into smaller sections, each with about same number of cells. During each split, an algorithm picks a dividing line and tries to keep closely connected parts on the same side to reduce the number of connections crossing the line. Objective. The main objective is to minimize the number of cuts or interconnections between partition, as this interpartition connection can lead to longer wears and increased delay. Balancing cells. Min cut placement also strives to balance the number of components in each partition. This balancing is important because it prevents one area from becoming congested while another has unused space. Hierarchical refinement. Min cut placement is a hierarchical approach. Each subregion is further divided until each partition is small enough that detailed placement technique can be applied to finalize the exact location of cells within each region. And advantages and application. Min cut placement is well suited for large designs and can handle hierarchical structure efficiently. Tools like Capo, which is popular min cut placer, are used to achieve routable placement, especially in design with high density and many fixed obstacles. This is a diagram. Each area is divided like this. First, divided into two parts. Now this area is divided into this part and this part. Now this part is, this square is divided into 1 and 2, and this is like this like this. In this way, similar here. Now this area is divided by this and this in two part, and this total area is divided into this and like this. In this way, it's done. So basically, it's divide the area and balance the number of components in each region so that the crossover connection is reduced, and it meticulously try to use all the sections so that it doesn't happen that one section is congested and another portion is less dense. We try to balance out the number of components. There are two approaches to divide the layout. Another is alternating cut line direction and repeating cut line direction. So alternating cut line directions is a technique in partition-based placement where direction of cut lines alternates between horizontal and vertical during recursive partitioning. The designing area is split into regions, ensuring a balanced distribution of cells in both axes. By alternating the cut line direction, the method avoids skewness, maintains compact layout, and reduces wear length. Closely connected components are grouped to minimize routing congestion. This structured placement simplifies later stages like legalization and optimization. It's especially effective for large complex circuit with dense interconnection, like alternating cut line direction like this one. The total area is first cut into these two halves. Now, this first cut, in this area, it's cut like that. That is 2A and that is 2B. And later, in this zone, it's like similarly here like this. It's cut into half again. And these two zones are cut into half like this, and this like that. Similarly, if you follow the numbering, you can easily understand which one coming earlier, which one coming later. 1, 2A, 2B, 3A, 3B. This area is like 3A, 3B, this way. So 4A, 4B, 4C, 4D, 4E, 4F, 4G, 4H. This way, connections. If you follow the numbering, 1, 2A, 2B, 3A, 3B, 3C, 3D, this way, you can understand how this cutting are done. Now, repeating cut line direction. Repeating cut line direction is a technique in partition-based placement where same cut line direction, horizontal or vertical, is used repeatedly during multiple levels of recursive partitioning. This approach divides the design area into increasingly smaller regions along a single axis, creating elongated partitions in one direction. It may simplify some placement strategies but risk uneven distribution, potentially increasing wear length and routing congestion. Repeating cut line direction can be suitable for designs with specific constraints like high connectivity along one axis. However, it's less commonly used compared to alternating cut line direction due to its limitation in achieving balanced layout. It's much more customized, like if there is a need that connectivity along one axis is more, then this repeating cut line direction is used. It's not alternative. Like first one horizontal line, it is cutting the whole area into this and this. Again in this rectangle area 2A, and here in this rectangle lower to rectangle it's 2B. It's done. Now it's completely done in this way. Now it's coming like now vertically in one direction we are doing like this, and next so in one direction it's going. First in one direction, once it's completed, then vertically it's getting done. Not alternating, repeating cut line direction. So these two slides on mean cut placement. Now we will move to the next slide, that is analytic placement. Analytic placement is a technique in chip design that uses mathematical optimization methods to determine the location of circuit components on a chip. The goal of analytic placement is to minimize an objective function usually related to the circuit's performance, such as total wear length or delay, by treating the placement problem as a mathematical optimization task. So key aspects of analytic placement are like optimization based approach. So analytic placement relies on mathematical optimization methods like numerical analysis or linear programming. Unlike heuristic method, it formulates placement as an objective function and seeks to find optimal configuration of cells to minimize the function. The approach involves treating placeable object like cells as dimensionless points initially, which simplifies the mathematical calculations. Next, objective functions. The most common objective function in analytic placement is wear length minimization, often using a quadratic function, that is squared Euclidean distance, to approximate the total wear length. Quadratic wear length models make it easier to apply mathematical techniques, but other functions such as nonlinear ones may be used for greater accuracy. In addition to wear length, other objectives like minimizing circuit delay, reducing congestion, or achieving better timing are sometimes considered. So these are the objective functions. And now two main stages in analytic placement, like global placement. It's the first stage where cells are positioned to minimize the objective function across the entire layout. At this stage, overlaps are allowed and cells may form clusters. And next, detailed placement. In second stage, cells are moved slightly to remove overlaps and achieve legal positions while keeping objective function optimized. Fourth is convex optimization and convexity. In quadratic placement, the placement problem often becomes a convex quadratic optimization problem. Convexity ensures that any local minimum solution is also a global minimum, making it possible to solve the problem efficiently by setting the partial derivatives of objective function to 0. Analytical placement uses mathematical optimization methods to determine the location of the circuit components on a chip. Mathematically, it determines the position. Goal is to minimize the objective function such as wear length or delay by treating the placement problem as a mathematical optimization task. So these are the key objectives. So additional techniques for spreading. After initial analytic placement, cells may be too close to each other, creating overlap. Dedicated technique like cell spreading are applied to ensure non-overlapping placement. This involves redistributing cells to avoid congestion while preserving the optimization of objective function. Main objective is to position the cells in such a way that in routing, the length could be less. Length is less means power loss is less, heat generation less, timing is less. So positioning is the key, and then how to optimize their position and so that there is no congestion, routability is easier. This situation is so critical because number of components are huge and complex connection between them because the functionality is complex. Day by day, number of devices are increasing and a chip is performing more and more complex work. So connections are complex. That is the reason why one approach after one approach is used. Depending on which kind of problem is in hand, it's chosen. Like in mean cut situation, we have seen if highly dense problem is there, then alternative mean cut is used. If density is in one axis, then alternative is not used, the other one is used. So depending on the problem and how to achieve it, depending on the problem and how to achieve the optimization, we choose our approach. Types of analytic placement. Quadratic placement uses a quadratic cost function which emphasizes minimizing longer connection. Quadratic placement is efficient and scalable. Nonlinear placement uses more complex nonlinear functions to represent interconnects, providing better accuracy, especially for components with diverse sizes, but it can computationally slower than quadratic methods. We have already mentioned in earlier that nonlinear placement is much more accurate result because it's more computationally intensive, and more intense computation means slower. So result will come in longer time. And advantages and limitation. Advantages: analytic placement is systematic, scalable, and provide highly optimized result for well length and other performance metrics. It is also suitable for very large design due to its mathematical rigor. It's very rigorous. And the limitations: analytic methods may require complex handling for real-world design constraints such as routing, congestion, or timing requirements. Some methods, particularly nonlinear optimization, can be slower and require careful tuning for stability. Analytic placement is widely used in EDA tools because it provides an efficient, scalable way to produce high quality placements that lay the foundation for effective routing and timing optimization. Why analytic placement matters? As chip design grow increasingly complex, the need for precise and efficient placement methods has never been greater. Analytic placement provides the mathematical rigor and computational power needed to meet modern design requirements, ensuring faster, smaller, and more power efficient chips. With its blend of theoretical elegance and practical impact, analytic placement remains a cornerstone of VLSI design, driving innovation in one of the most challenging engineering domains. These might be very resource exhaustive methods, time requiring methods, although EDA tools widely used methods because that gives a much more accurate result. That's why these methods are so appreciated and followed in EDA tools. Now next topic, like simulated annealing. Simulated annealing is a heuristic optimization technique used in placement algorithm, particularly in the global placement phase of VLSI design. It mimics the physical process of annealing in metallurgy, where materials are slowly cooled to minimize internal energy and achieve a stable configuration. The following are key aspects of simulated annealing placement. Basic principle: cost function. Placement quality is evaluated using a cost function which combines factors: well length, often computed using half perimeter well length metric; cell overlap, quantifies overlap between cells, penalizing large overlap more heavily; row inequality, penalizes deviation in row lengths which could cause inefficiencies. Next, this is cost function. And next, cooling schedule. The process starts at high temperature, allowing more random placement changes. As the temperature decreases, the algorithm becomes less tolerant of changes that increase cost. The temperature is reduced using a cooling factor alpha, which may vary during the process. There is basically analogy. Simulated annealing, the method simulated annealing, the analogy is used here. It's a cooling factor is there, that is initial phase; high cooling rate, that is alpha is 0.8 to explore configurations broadly. Middle phase, slower cooling, alpha is 0.95 for fine tuning. Final phase, rapid cooling, alpha 0.8 for convergence. At high temperature, it's more random placement changes are allowed closely, more like it's a small factor, that is alpha or cooling factor is tuned, and the design reaches to more fine tuning, that is simulated annealing. Algorithm steps: initialization. Begin with a high temperature and random initial placement of cells. Placement perturbation: modify the placement by moving or swapping cells to generate new configurations. cost evaluation, calculate the cost of new placement. If the new cost is lower, accept the change. If the cost is higher, accept the change with a probability based on current temperature and cost difference. And iterative cooling, reduce the temperature and repeat the perturbation and evaluation steps until the system freezes, that is temperature reaches a minimum threshold. This is the algorithm steps. Now equilibrium, at each temperature level, the algorithm runs enough iterations to achieve equilibrium, ensuring stability before cooling further. Now application effective for standard cell placement in design with constraints like limited feed through cells or uneven layout, advantages flexibility in handling complex cost function, and ability to escape local minima by accepting worse solution at higher temperature, and challenges computationally intensive due to large number of iterations, parameter tuning, cooling schedule, acceptance ratio requires expertise. Example tool Timberwolf, a popular placement tool using simulated annealing, incorporates detailed cost function and strategies for cell spreading, overlap minimization and optimization for varying direction. This method is a robust approach for achieving high quality placement in design of integrated circuit. Now global placement. This is floor plan. Now placement, global placement, legalization, detailed placement. Now after that CTS and routing. In global placement, placing standard cell. Now global routing, and this is more refined detailed routing. In global placement, components like cells and circuit modules are assigned approximate locations across the layout area. The primary goal at this stage is to minimize the cost function related to wear length or timing constraints without enforcing exact legal positions or preventing overlaps. Optimization without exact position, components are placed to minimize interconnect length and congestion, but position are not finalized. Independent X and Y optimization, placement simplifies the process by optimizing cell locations separately along X and Y axis. And use of mathematical models, quadratic or nonlinear models are used to achieve optimal placement. Preliminary layout provides a rough layout, leaving exact overlap-free positions for detailed placement, and foundation for legalization serves as a starting point for legalization and detailed placement to finalize a feasible and efficient layout. Now, global placement is crucial for creating an efficient starting point for further optimization that lead to a functional and high performance chip layout. So global placement is basically the starting point. After that, legalization will happen. The cells or the modules will be arranged in grids along rows, and then power connection will be given done. More fine tuning of connections will be get done. So this global placement is the starting point. Now legalization. This diagram is self-explanatory. Global placement, those modules are placed, although there are overlapping. In legalization, they are arranged in a very orderly manner. No overlapping is there. So legalization is a process that adjusts the positions of circuit components or cells on a chip layout to ensure they meet specific physical design constraints. So this diagram is self-explanatory. After the initial or global placement, components may not align to designated legal positions such as rows or grid points, and may even overlap. Legalization corrects these issues by moving cells to valid positions while minimizing disruption to the optimized layout. Key aspect of legalization: aligning to legal positions, removing overlaps, and minimizing disturbance. Cells are moved to specific legal sites, often aligning with power rails and rows. This ensures that design complies with the manufacturing requirements, which mandate cells to be placed at predefined locations to ensure proper connections and spacing. Now, removing overlap. During global placement, cells may be placed too close each other, creating overlaps. Legalization removes this overlap by shifting cells slightly while trying to maintain the overall structure and objective of the initial placement. And final and third, minimizing disturbance. Legalization aims to make only minimal adjustment to the positions of cells to preserve the optimized parameters like wear length or timing achieved during global placement. Excessive movement can increase wear length, affect timing, and create new congestion. So algorithms are designed to balance legality legality with minimal disruption. So aligning to legal positions, first step. Next, removing overlaps and minimize disturbance. Legalization aims to make only minimal adjustments so that the overall initial placement doesn't disturb much. Optimize parameters like wire length or timing that achieved during global placement that is not disturbed. That should be preserved. Excessive movement can increase wire length, affect timing, and create new congestion. So algorithms are designed to balance legality with minimal disruption. Now, handling physical constraint. Legalization accounts for physical design constraints such as spacing rule, row alignment, fixed cell localization. It also adapts different size components including standard cell and large macro blocks. Legalization algorithm. Common algorithms for legalization include greedy algorithm, quickly place each cell in the nearest legal position but may need refinement for optimal result. Next, sliding window or branch and bound works for reordering and slightly shifting cells within a defined window to achieve legal placement. Dynamic programming and linear programming. These techniques offer more systematic approach to legalized placement, especially for complex layout with mixed cell sizes. Now, integration with detail placement. Legalization is often followed by detail placement, a fine-tuning stage where small adjustments further optimize the layout to improve performance metrics such as reducing wire length and improving timing. And what is the importance of legalization? Legalization is critical because it ensures layout complies with all physical design rules and manufacturing constraints while retaining as much as optimization from global placement as possible. This step is necessary before routing as a legalized layout provides a reliable foundation for connecting the components without further conflicts or overlap. That is the importance of legalization. Now, detail placement. Detail placement follows global placement and legalization. During detail placement, the precise positions of circuit cells are fine-tuned to improve design metrics like wear length, timing, power, and congestion. This stage aims to enhance the quality of the initial placement by making minor adjustments to cell positions without violating legal constraints by avoiding overlapping and maintaining alignment to rows. So, key aspect of detail placement: fine-tuning cell position, optimizing wear length and timing, congestion and density management, and there are some improvement techniques mentioned like detail placement fine-tunes the global placement layout by making minor localized adjustment to enhance design quality while staying close to the original configuration. Optimizing wear length and timing. The main goal of detail placement is to minimize wear length, reducing delays and improving timing, especially along critical paths. Congestion and density management. Congestion arises from densely packed cells causing routing issues. Detail placement algorithms spread cells to ease routing and prevent hotspots. So global placement like this, and in detail placement they are very ordered, the connections. Now cell swapping, exchanging the positions of neighboring cells to reduce wear length to improve timing. Cell sliding and shifting, adjusting cells slightly within rows or gaps to optimize spacing and align with power rails or tracks. Group movement, moving groups of cells within a sliding window to improve alignment and reduce wear length. So these are some cell swapping, cell sliding and shifting, group movement. These are some improvement techniques. Window-based optimization. Detail placement is often performed within a small localized windows or regions to reduce computational complexity and allow more focused optimization. Its focus is on smaller windows, smaller localized zones. The algorithm may reorder cells within these windows to minimize disruption to overall placement. Overall placement remains same, which is achieved during global placement. Detailed placement is more like a fine-tuning for a localized area. Handling unused space. If there is unused space between cells in a row, detailed placement may shift cells slightly to either side or distribute them evenly, ensuring that no gaps lead to wasted area. Ensuring legalized placement. Detailed placement adheres to legal positions determined during legalization, maintaining cell alignment and spacing to prevent design rule violation. Importance of detailed placement. Detailed placement is crucial because it provides the final adjustment needed to optimize performance metrics before the routing stage. By fine-tuning the positions of cells, detailed placement improves wear length, timing and congestion, resulting in a more efficient and high-performing chip layout. So, detail placement is crucial because what we are achieving in global placement and doing legalization, that is more finely tuned in this stage, and this way we improve wear length, timing, congestion, so that the layout becomes more efficient and high performing chip layout. So we are done with this slide. We are done with our today's episode. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and global routing. Next, detailed and specialized routing. Today in this episode, we will discuss mostly about global routing, although detailed and specialized routing are another two types of routing. We will give a touch base on that. So this slide is about that. So this second slide is about touch base of detailed and specialized routing. And after that, essential terminology for global routing. Here we will learn some technical terms that is related to global routing, so that in later slides when we discuss it in detail, we don't get stuck. After that, what is switchbox in routing? Switchbox is another terminology that is introduced in routing, and there are 2D and 3D switchbox are there. So here in this slide, we will understand in detail what actually switchbox is. Next, optimization goals in global routing. After that, representing routing regions. Routing region is another new terminology. In this slide, we will discuss how routing regions are represented and global routing flow. So there are some sub-steps of global routing process. Here we will learn that. And next, single net routing, global routing in connectivity graph. Finding shortest path. There are two algorithms discussed here, Dijkstra's algorithm and A-star search. These two algorithms are discussed here. Next, full netlist routing. Global router. This is not about any specific router. This is a generalized idea about a global router, how it works, what are the main components or methodologies used. And finally, optimization for different design types, full custom, standard cell and gate array. So these are the pointers we will discuss in today's episode. We are done with this slide. We will move to the first slide. Design flow and global routing. This is the infographics we are using in the episodes based on backend. VLSI design flow starts with system specification, then architectural design, functional design, logic design, circuit design. After that, physical design. Once we get the synthesized netlist, after that, whatever we do, that is part of physical design. And physical design is not a single step. There are partitioning. We have done placement as a part of chip planning, floor planning, and ground and power pin routing. That is also done. Clock tree synthesis. We have an episode on clock tree synthesis and another episode on what is clock tree. We have both episodes to give a good idea about clock tree and synthesis of clock tree. And now signal routing. So signal routing has 3 steps: global routing, detailed routing and specialized routing. In this episode, we are concentrating on these global routing. So in VLSI, routing is a crucial step that connects the various components like logic gates, transistors and memory cells on a chip. It involves determining the paths for electrical connections which are implemented through metal layers on the chip. In partitioning, area is partitioned. In placement, modules are placed. Now they need connection. How that is done, that method is called routing. So it involves determining the paths for electrical connection which are implemented through metal layers on the chip. And routing is divided into 3 major steps: global, detailed and specialized routing. Global routing is basically the initial stage of routing. Detailed routing is more detailed, and in specialized routing, special signals like clock signal taken care of. Global routing, initial stage of routing process where the chip's overall routing framework is determined. It defines the general paths for each connection or net without focusing on precise details. The goal of global routing is to create an approximate plan for how the nets will be routed across the chip. That is global routing. It's the initial step. And what are the key aspects of global routing? Calculates the approximate net paths and assigns them to regions or grids within the chip. Allocates appropriate metal layer for detailed routing without specifying exact geometry. Prevents congestion by ensuring sufficient routing space for all nets. Divides the chip into grids, systematically determining regions for each net. Focuses on optimizing overall interconnection layout rather than precise routing geometry. After global routing also, there are quite a good scope of improvement, and that is done in detailed routing. Global routing is the initial stage. Here we decide the framework, allocates metal layers although doesn't specify the exact geometry, try to prevent the congestion by ensuring sufficient routing space for all nets, divides the chip into grids systematically just to keep the region for each net and optimizing overall interconnection layout rather than precise routing geometry. So that is the overall key aspects of global routing. We are done with this slide. We will move to the next slide. This episode is dedicated for global routing. Since we have mentioned, just we are giving a touch base about detailed and specialized routing. In later episode, we will discuss these two types of routing in detail. Detailed routing, this stage refines global routing into precise manufacturable paths, finalizing the layout of electrical connections for fabrication. Key aspects of detailed routing. Detailed routing defines precise wire paths while adhering to design rules, including spacing, width, via placement, and metal layer usage. It optimizes wires, ensuring signal integrity by minimizing RC delay and crosstalk, and resolves congestion by redistributing wires or using alternative layers. Special attention is given to power and ground routing to guarantee reliable voltage delivery across the chip. These are the key aspects. What it does, it defines precise wire path while adhering to the design rules. It strictly follows the design rules. Design rules are set by the fab lab, that fabrication unit. We have to follow it. Whenever design is there, before tape out, DRC clearance is absolutely necessary. Otherwise, the design or the GDS2 is not manufacturable. These are the bare necessary geometry that is mentioned here, and we have to adhere by that. In detailed routing, it follows strictly design rules, including spacing, width, via placement, metal layer usage, everything. All data are there, the strict rules are there, and it follows these rules. This optimizes vias, ensures signal integrity by minimizing RC delay and crosstalk, and resolves congestion by redistributing wires using alternative layers. Special attention is given to power and ground routing to guarantee reliable voltage delivery across the chip. And now specialized routing. Specialized routing handles net with specific requirements such as clock, power network, high-speed signal, ensuring they meet performance constraints. So special net, special care, and specialized routing. Key aspects of specialized routing. Specialized routing includes critical net and clock routing, ensuring precise timing and reliability. It also covers power and ground distribution, high-speed signal routing, and shielding for noise reduction. This ensures optimal performance and signal integrity in complex design. So these are key aspects of specialized routing. So here, that much we are discussing about detailed and specialized routing in this episode. In later episode, we will discuss these both topic in detail. So we are done with this slide. We will move to the next slide. Essential terminology for global routing. So these are the some important terminology. We will use them later. So let's try to understand what it means. A routing track. A routing track represents a horizontal or vertical wiring path that facilitates the routing of signals. Signal net traverse these paths by alternating between the horizontal tracks and vertical columns connected using interlayer vias. So it's talk about routing tracks. This diagram shows horizontal routing channel. This area, if cells are there, standard cells are there, this area is highlighted here, how these look like. So routing region. A routing region is a defined area containing routing tracks or columns. It serves as the guide for allocating wiring paths to connect signal net efficiently. So a routing region is defined area containing routing tracks or columns. It serves as the guide for allocating wiring paths to connect signal nets efficiently. So routing track and routing region. Now uniform routing region. This region consists of evenly spaced horizontal and vertical grid lines forming what's known as global grid or grid. The grid comprises unit cells called global cell or G cells. Typically, the spacing between grid line ranges from 7 to 40 routing tracks, balancing the complexities of chip scale global routing and detailed routing task. Non-uniform routing region. Unlike their uniform counterparts, non-uniform regions are defined by boundaries aligned with external pin connections or macro cell edges. That region includes channel and switch boxes of varying dimensions. Now channel. A channel is a rectangular routing region designed to connect pins located on its two opposite sides. While the other two sides remain pin-free, channels are further classified as horizontal channel, vertical channel. Features pins along the top and bottom boundaries, and vertical channel features pin along the left and right boundaries. So horizontal channel pins are above and below, and if the channel is vertical, obviously that will be on the both sides, that is right and left boundaries. G cell or global cell or G cells are the fundamental units within global grid. They serve as basic building blocks for defining paths in routing regions and are instrumental in routing process. So these are the terminology: routing track, routing region, uniform routing region, non-uniform routing region, channel, that is horizontal and vertical channel, G cells or global cells. These are the important terminologies. We are done with this slide. We will move to the next slide. What is switchbox in routing? A switchbox is a square or rectangular region where multiple channels intersect. This critical structure enables connections between different routing tracks or columns, enhancing the routing network's flexibility. So switchbox is basically a junction. Multiple channels intersect. That is a switchbox. Here it's shown switchbox routing between horizontal and vertical channels of a macro cell. In this region, both vertical, this is horizontal channel, this is vertical channel, they meet, and in all sides the routing is done. These interconnects are traveling from one side to other side. A 2D switchbox exists in a single plane. In this plane, that is a 2D switchbox. A 2D switchbox exists in a single plane and connects horizontal and vertical routing channels within the single metal layer. It serves as a connection hub in a single metal layer, because in a chip, if that is the cross section vertically, like these multiple layers of metals are there and vias are vertically connected, connecting one layer to another, like that only. And for a 2D, and it's basically 3D on, I don't know whether you can understand my drawing. This way. These vias are vertical on any plane, any horizontal plane, and in a 2D switchbox that is in one single plane, it exists on a single plane and connects horizontal and vertical routing channel within that single metal layer. It serves as a connection hub, enabling routing. I said it's like junction. It serves as a connection hub, enabling routing paths to switch directions, that is horizontal to vertical or vice versa, within a specific routing layer. In a specific routing layer means in specific metal layer or a specific plane. Frequently used in PCB design or simpler VLSI design where interlayer routing is minimal or non-existent. The region typically resembles a rectangular or square grid with intersection points for connecting different channels. A 3D switchbox incorporates connection across multiple layers of a chip, often through interlayer vias. It facilitates interconnections not only between horizontal and vertical tracks but also between different metal layers. This capability is crucial for modern multi-layered ICs. This is shown as a 3D structure, metal 5, metal 4. So here if we consider it's a 3D switchbox. It facilitates interconnection not only between horizontal and vertical tracks but also between different metal layers. This capability is crucial for modern multi-layer ICs widely used in advanced VLSI designs where chips have multiple layers of metal routing such as in 3D ICs or multi-layer ASICs. Extends the concept of 2D switchbox to include vertical pathways allowing signals to traverse different physical planes within the chip. That is 3D switchbox. So we are done with this slide. We will move to the next slide. Optimization goals in global routing. Minimizing total wear length, managing routing congestion, maximizing timing slack, balancing via usage, optimizing for power efficiency, adapting to design constraints. So these are the optimization goals. So minimizing total wear length, that is the first one. Wear length minimization is fundamental goal in global routing or any design because reducing the total wear length enhance performance, heat is less, the signal will travel less path, so delay will be less. Shorter wears reduce signal propagation delay leading to faster circuit. Less wear length means reduced capacitance and consequently lower power dissipation. Shorter interconnects decrease the chances of defects and increase manufacturability. Managing routing congestion. Congestion arises when multiple signal nets compete for the same routing sources. Effective congestion management ensures efficient resource utilization, prevents overloading specific regions while underutilizing others, avoids unnecessary detours that can increase wear length and delays, reduces the risk of violating constraints such as spacing between wears. Maximizing timing slack. Timing slack refers to the difference between required arrival time and the actual arrival time of a signal. Maximizing timing slack is crucial for meeting timing constraints. That ensures that all signals arrive within their designated time windows, provides a buffer against variations in manufacturing or operational conditions. So time slack is required for meeting timing constraint. So that ensures that all signals arrive with the designated time windows, provides a buffer against variation in manufacturing or operational condition. And balancing VI usage. VIA connect different metal layers in a chip's layout. Excessive VI usage can increase manufacturing costs, lead to reliability issues due to thermal stress, and delays by introducing additional resistance and capacitance. Balancing VI usage is therefore vital for cost-efficient and reliable designs. Optimizing for power efficiency. Power optimization is critical, especially for portable devices and data centers. Efficient global routing minimizes dynamic power by reducing switching activity and interconnect capacitance, minimizes static power through efficient use of routing resources to minimize leakage. And now adapting to design constraint, modern VLSI design face constraints like fixed die boundaries, specific routing resources, and predefined placement. Optimization ensures that these constraints are respected without compromising the overall design quality. So these are the optimization goal of global routing. Now we will move to the next slide. Representing routing regions. In global routing, channels and switchboxes are represented as graph, where nodes represent routing regions and edges represent adjoining region. There are three graph techniques. One is grid graph, second is channel connectivity graph, third is switchbox connectivity graph. So this is the layout and its grid graph representation. It's divided into equal grids and each grid cells are numbered 1, 2, 3, 4, 5 like that. So also defined as global grid or G grid. A uniform grid overlays the chip layout. It consists of horizontal and vertical grid lines that divide the chip into smaller cells known as global cells, and grid lines are fixed at regular intervals to balance global and detailed routing complexity. That is grid graph. Second is channel connectivity graph. Graph that is function of V and E, where nodes V belongs to capital V represent channels and the edges E represent adjacencies of the channels. Capacity of each channel is represented in its respective graph node. So the same design, these are the channel and these are the free zone, the channels. 1, this is second channel, this is third, fourth, fifth, sixth, and now connection is like that. So 1 to 4 can be done through this way, and 3 to 4 is connected, 3 to 8 is connected this way. That is layout and channel connectivity graph. And now switchbox connectivity graph, where these nodes V represent switchboxes and each an edge exists between two nodes if the corresponding switchboxes are on the opposite side. So switchboxes, the nodes represent switchboxes. These are the nodes. Nodes represent switchboxes from where it's crossing, like this way and that way. That one crossing, that's one second crossing, third crossing, that could be a crossing, that is another crossing from here and there, that is crossing of these and that, 2 to 6 and this way. It's all crossings. So switch boxes, and an edge exists between two nodes if the corresponding switch boxes are on opposite sides of the same channel. This is a channel and these opposite side of same channel, and the edge between these two that is connected when an edge exists between two nodes. These two nodes, if the corresponding switch boxes, this one switch box and these two switch box, they are situated just opposite to each other. That is switch box connectivity graph. These are three representation: grid graph, channel connectivity graph, and switch box connectivity graph. So we are done with this slide. We will move to the next slide. So global routing flow. Okay, so first is defining the routing regions, and there are some steps like partitioning the layout area into routing regions, allow nets to be routed over standard cell in some cases, and structure the routing region as 2D or 3D channels, switchboxes or other region types. Now represent the region along with their capacities and connections as a graph. Now step 2 is mapping nets to the routing region. Provisionally assign each net in the design to one or more routing region to connect all the pins. Now ensure the number of net passing through routing region does not exceed its routing capacity. Consider timing and congestion as factors influencing the path selection for each net. And third is assigning cross point. Assign routes to specific spots or cross points along the edges of routing areas. Align cross points to simplify handling design designed with millions of cells, enable faster processing through parallel and distributed methods by allowing independent work on each routing area. Analyze the dependencies between net connections and the order of routing channels to optimize cross-points assignment. These are 3 steps by which global routing flow is done. So we are done with this slide. We will move to the next slide. Single net routing. A set of pins that electrically connected is called net. A single net routing task deals with routing one such net at a time, ensuring it adheres to design rules while optimizing for factors such as wire length, timing, and congestion. For a 2-pin net, the task is relatively straightforward, requiring a path between the 2 pins. For a multi-pin net, the net is decomposed into smaller 2-pin subnets before routing. So, objectives of single net routing is minimizing wire length, reduce the total length of the wire connecting pins, minimizes delays and power consumption. Adhere to design rules, ensure the route meets constraints like spacing, via limits, and layer assignment, and avoid obstacles, navigate around fixed blocks, macros, and other routed nets. Optimize timing. Critical nets must be routed with minimal delay to meet performance requirements. So these are objectives of single net routing. Now techniques for single net routing. Rectilinear spanning tree. A rectilinear spanning tree connects all terminals, that is pins, using only direct pin-to-pin connections with vertical and horizontal segments. These connections are restricted to meet exclusively at pins, meaning that crossing edges do not intersect and no additional junction points are introduced. When the total length of the segment is minimized, it's called rectilinear minimum spanning tree, that is RMST. It's a direct pin-to-pin connection. There is an example, P1 to P2, it's a direct connection, and P2 to P3, another direct connection. Otherwise, P1 to P2 can be connected like this, and P2 to P3 is straight like that only. And rectilinear stainer tree, that is RST, that is a little bit different. A rectilinear stainer tree connects all pin locations, and many include additional locations called stainer points, this one. While any rectilinear spanning tree for a P net qualifies as an RST, introducing strategically placed stainer points can often reduce the total net length, and RST becomes a rectilinear stainer minimum tree, that is RSMT, when the total length of the segment used to connect all pins is minimized. Like from P1 to P2, if we introduce one stainer point, from there only we can draw this another connection, like P1 to P2 through S1, and from S1 it's connected to P3. These are rectilinear spanning tree and rectilinear stainer tree. These are techniques for single net routing. We are done with this slide. We will move to the next slide. Global routing in connectivity graph. Global routing using a connectivity graph that is done by following different steps like defining routing region, defining the connectivity graph, determining the net order, assigning tracks for all pin connections, and global routing of all nets. So these are the steps. The vertical and horizontal routing regions are formed by stretching the bounding box of all cells in each direction until a cell or chip boundary is reached. So if these are the region of a cell, so from here in the next diagram we can see that there is it's stretched like that. From here it's stretched like this. From here it's stretched like this way. Defining the connectivity graph. In connectivity graph, nodes represent routing regions, edges indicate their continuity, and each node stores the horizontal and vertical capacities of its region. So in this way, horizontal and vertical macro cell edges are extended to form the routing region. So routing regions is defined. Now routing regions is represented by routing graph. So this is a defined one, the same design, the same layout actually, and now it's converted into a vertical capacity, horizontal capacity are mentioned with the nodes. So each node stores the horizontal and vertical capacities of its region. So this way it's represented as a routing graph. Now determining the net order. The order of net processing can be set before or during routing based on factors like criticality, pin count, bounding box size, that is larger gets higher priority, or electrical properties. Some algorithms adjust dynamically based on layout characteristic observed during routing. Now, assigning tracks for all pin connection. A horizontal and vertical track are reserved in each pin's routing region to ensure connectivity. And final, global routing of all nets. Each net is processed sequentially involving steps such as net or subset ordering neighboring track assignment using maze routing algorithm and capacity updates in the connectivity graph. Substeps through which global routing is represented in connectivity graph. So we are done with this slide. We will move to the next slide. Finding shortest path, Dijkstra's algorithm. This algorithm finds shortest path from source node to all other nodes in a graph. Work with graphs that have non-negative edge weights commonly used in maze routing and shortest path problem. So this non-negative edge weight is a prerequisite of this method. About parameters, graph with non-negative edge weights, source node is as the starting point and target node as the destination. Node groups, there are 3 groups. Group 1 or unvisited nodes. So nodes that have not been visited is unvisited node and grouped as a group 1, and next group 2 is considered nodes. Nodes is visited but shortest path cost not finalized, and group 3 is known and finalized, like nodes for which the shortest path cost is determined, that is in group 3, third group. So optimization objectives are geometric distance, routing congestion, electrical properties and weight densities. These are the optimized objectives. And algorithm initialization, all nodes starts at group 1. The cost of reaching each node is to set to infinity except for the source node which has cost 0. That has a cost 0. This is the source and this is the target. The cost of reaching each node is to set infinity, and except for the source node is 0. Parent of each node is initially unknown. The source node is moved to group 3 as the first known node. Value set to is 0 and its cost is known. So we will first move it to third group, that is known nodes. From there, we will start to solving the problem. The algorithm execution while the target node F is not reached. Compute the cost of reaching neighboring nodes from current node. So from A, we can move either towards D or towards B. If we move towards D, the cost is 1, 4, and if we move towards B, it's 8 and 6. Less costly path is A to D. So we will consider this one. This is the first we will consider. A will move to group 1 and A, parent of D, this will move to group 2. If node is already in group 2, compare and update its cost. If a better or lower cost path is found, select the lowest cost node in group 2 and move it to group 3. Repeat until the target node is added up to group 3. This is the method. In next slide, we will see how we can do it. So these are the prerequisite knowledge we need to understand Dijkstra's algorithm, like input parameters, node group, optimization, objective, initialization and execution, how it's done. So we are done with this slide. We will move to the next slide where we will discuss how we can do it. So path reconstruction, first A to D. A is first moved to group 3 and now A to D. A to D is 1, 4, A to B, 8, 6. So we will move this. This is the short, in between these two, this is shortest path or least costly path. So it will move to here. From D to G, if we want to go, it is 8, 8, D to G 8, 8, although the previous value is will get added. So it will become 8 plus 1, 9 and 8 plus 4, 12. Look, D to G, that is 9, 12. We keep it here only. Now here let's try to go from this side. A to B, that is 8, 6. That is known. So A, B, 8, 6. Now from B to E, value of B is 8, 6. That is getting carry forward. B to either we can move from B to E or B to C. B to E would be 8 plus 2, 10 and 6 plus 6, 12. Another one is B to C is from here, this is the cost, and from B to C, that is 8 plus 1, 9, A 6 plus 10, 6 plus 4, 10. B to C, 9, 10. Obviously, this is most costly, so we will keep it and it's not accepted. And from D, there are two paths. We will move to E, so 9 plus 1, 10, 7 plus 4, 11. And from D to G, that is 8 plus 1, 9, 8 plus 4, 12, 9, 12. So D to E and D to G, lesser value is like D to G, 9, 12, not 10, 11. So A to D, now D to G. And obviously G to T is small. So this is the path. So D to E is as considered as this one, and A to B is also known. So we moved it to group 3. B to C is known and accepted. B to C 9, 10. Now E to F, 18, 18, 12, 19, cost is increasing. So E to H and C to F, these are very costly. So we are not accepting it. Rather, G to H is 12, 14, G to H, D to G is 9, 12, and here it's 9, 12, and 9, 12 plus 3, 2, that is 9 plus 3, 12, and 12 plus 2, 14. This is a very small example of a graph. If we consider, so this is the least costly path, so we will move from S to T, that is A to H, through this path, A, D, G, H. Path reconstruction 1, F is found, backtrace from F to S using parent node to determine the shortest path. Efficiency consideration, each iteration only consider neighbors of the most recently added node, current node, reducing redundant calculation. Nodes move sequentially into group 3 based on the increasing order of their shortest path. The algorithm stops when the target node is added to group 3, ensuring an optimal path. Handling node cost, when nodes have traversal cost, each node is replaced by d-click, a complete subgraph of d. Click edges have weights equal to the original node cost. The original d incident edges are connected to different click nodes. This transformation ensures that path traversal accounts for node traversal cost efficiently. So this is the method. We keep on adding the value of the previous edge to the next node, and this way we go, because it's get added. Once we start moving, it's get added. So this is the least costly path. We will accept this one. We are done with this slide. We will move to the next slide. That is A star search. So finding shortest path, A star search. Similar to Dijkstra's algorithm but extend the cost function. Includes an estimated distance from current node to the target, guarantees the shortest path if path exists. The estimated distance should never exceed the actual distance. Admissibility criteria are efficient compared to Dijkstra's algorithm, expands only the most promising nodes, best first search. Reduce the solution space comparing to Dijkstra's algorithm. A tight lower bound estimate can significantly improve runtime. Can be derived from Dijkstra's algorithm by adding distance to target estimate and node priority to determine by sum of cost from start node like Dijkstra's level. Estimated remaining distance to the target. Bidirectional A-star search is a variant, expands nodes from both source and target until region is met. Reduces the number of nodes considered slightly. However, tracking the order of visited nodes along with complexity of implementing an efficient solution poses significant challenges. In practice, these difficulties can outweigh the potential benefits of bidirectional search. This is another method. It's quite similar to Dijkstra's algorithm but extend the cost function. And there is one bidirectional variant of this A-star search. Their nodes are expanded from both source to target until they meet each other. Whenever bidirectional method is there, so there always need to keep a track of the visited node. Along with complexity of implementing an efficient solution poses significant challenges in practice. These difficulties actually outweigh the potential benefits of bidirectional search. Methods of full netlist routing. There are two methods, integer linear programming and repup and reroute, that is RRR. A linear programming is a mathematical problem that includes a set of conditions called constraints and an optional goal or objective function to maximize or minimize. Both the constraints and the objective functions must be written as linear equations or inequalities. If all variables in linear program only take whole number values, it is called an integer linear program. When these variables are restricted to only 0 or 1, it's referred to as 0-1 ILP. There are various software tools like GLPK, Cplex and Mosaic that can solve linear programs. The ILP takes 3 inputs and width by height routing, grid G routing edge capacities and the netlist. The ILP uses 2 sets of variables. The first set includes k boolean variables, each representing an indicator for one of k specific paths or routes for a net in the netlist. The second set contains k real variables, each of which represents a net weight for a specific route for a net in netlist. That is integer linear programming. There are some tools, various software tools who can solve integer linear programs, and repub and reroute. Modern ILP solver can handle hundreds of thousands of routes efficiently, but commercial EDA tools require faster and more scalable methods. The repub and reroute framework addresses these by focusing on problematic nets. When a net faces obstacle or interference, RRR temporarily allows violations route all nets, then interactively removes and reroutes some to reduce conflicts. Alternatively, push and shove strategies move existing nets to new positions to resolve congestion or make unroutable nets feasible. A greedy routing approach avoids violations but often causes large detours. In contrast, RRR permits temporary overcapacity routing to optimize overall paths. Allowing violations and rerouting enables more efficient routing with fewer detours than strictly violation-free methods. In the RRR framework, not all violation nets are ripped up, reducing runtime significantly with only a small increase in well length. Alternatively, push and shove strategies may move existing nets to new positions to resolve congestion or make unroutable nets feasible. A greedy routing approach avoids violations but often causes large detours. These are two types of full netlist routing methods: integer linear programming ILP and repub and reroute, that is RRR. Now, global router. It's a generalized view of what a global router contains of. Global routing instance. Now, net decomposition, initial routing. If there is violations, then repub and reroute and go again for check for violation. If there is no violations, that will go to layer assignment and final improvements. So, a global router first divides multiple pin nets into 2-pin subnets and generates an initial routing solution on a 2D grid. If there are no violations, it assigns layers by mapping the 2D routes into a 3D grid. If a violation occurs, problematic nets are ripped up and rerouted iteratively until the design is violation-free or stopping conditions such as a CPU limit is reached. In the last slide, we have discussed how RRR works. A global router first divides a multiple net pin into 2-pin subnets and generates an initial routing solution for a 2D grid. If there is no violation, it assigns layers by mapping the 2D route into a 3D grid. If violation occurs, it only picks up the problematic nets that is ripped up and rerouted iteratively until the design is violation-free or a stopping condition comes. It only do for the problematic one. It's a case-specific thing. Some routers include an optional cleanup pass to minimize wear length after repub. Alternatively, some global routers route directly on 3D grid, which can improve wear length but is slower and may fail to complete routing. So nets are routed using maze and pattern routing with negotiated and congestion routing, managing cost. Global router determined path for 2-pin nets while adhering to capacity constraints, prioritizing minimal wear length. It employs maze routing methods like Dijkstra or Esta search to ensure the shortest path between points. However, these methods can be excessively slow, especially when topologies involve edges requiring minimal vias. Now, modern router implement RRR using negotiated congestion routing. In this approach, each edge is assigned a cost or value that represents the demand for that edge. Higher costs discourage nets from utilizing heavily used edges, indirectly encouraging them to explore alternative, less congested paths. So this is how a global router works. That is a philosophical representation of it. So we will move to the next slide, that is optimization for full custom design. A full custom design features a layout dominated by macro cells with irregular non-uniform routing regions. Key initial tasks include channel definition and channel ordering. Full custom design is dominated by macro cells with irregular non-uniform routing regions. Initial tasks include channel definition. Channel definition partitions the global routing area into routing channels and switch boxes. Channel ordering is determined using floor plan tree. If a part of floor plan cannot be represented using horizontal and vertical cuts, at least one switch box is used along with channels. Once all of the regions, channels and switch boxes are determined, the interconnects can be routed. So Steiner tree routing and minimum spanning tree routing are two methods used. Shortest path is determined by Dijkstra's algorithm. So this is the design. Now it's divided into regions represented by a graph. Now optimization for standard cell design. In standard cell design, when the number of metal layers is limited, feed-through cells are used to route a net across multiple cell rows if the cell rows and netlist are fixed. The number of unoccupied sites within the cell rows is also fixed, which restrict the number of possible feed-throughs. As a result, standard cell global routing aims to ensure the design is routable and identify a low congestion solution that minimizes the total wear length. So these are feed-through cells. It's used when metal layers are limited. Feed-through cells are used for optimization of standard cell design. Next is gate array design. In gate array design, the cell sizes and routing region sizes, that is routing capacities, are fixed. Since adding extra routing resources is not an option to ensure routability, key tasks involve assessing the placement's routability and finding a feasible routing solution. Additional optimization objectives include minimizing the total routed wear length and reducing the length of longest timing path. So here, cell size and routing region sizes are fixed. We cannot increase it. Comes in a package. Adding extra routing resources is not possible. So key task involves assessing the placement's routability and finding a feasible routing solution. What is available within that, we have to solve the routing issue. So additional optimization objective include minimizing the total routed wear length and reducing the length of the longest timing path. So this is the optimization for gate array design. So we are done with this slide and we are done with our today's episode. That we had all for our today's episode. Look at the pointers we are going to discuss in today's episode. First, design flow and detailed routing. In our previous episode, we have discussed about global routing. After global routing, there comes the step of detailed routing. So today that is our point of discussion. And next is different routing techniques. Horizontal and vertical constraint, zone representation. After that, horizontal and vertical constraint graph. Channel routing by left edge algorithm. Channel routing by dogleg routing. Next, switch box routing. After that, over the cell or OTC routing algorithm. Next is OTC routing methodology. And finally, modern challenges in detailed routing. So today we will keep our discussion over all these points. So we are done with this slide. Let's move to the next slide. So design flow and detailed routing. This is a diagram we are using in last few episodes based on physical design, and as we can see here, after system specification, architectural design, functional design and logical design, circuit design, these things are done. And then comes the physical design, and physical design consists of all this partitioning, chip planning, placement, clock tree synthesis. We have already covered all these steps. And then comes signal routing, and even signal routing, and there are 3 sub-steps: global routing, detailed routing and specialized routing for those specialized net which require more attention. And we have already covered global routing, so today it's detailed routing. In VLSI, routing is crucial step that connects the components of a chip. So there are multiple components on a chip and they are connected to realize the intended function for which the chip is designed, and that connection is done by routing. So it involves determining the paths for electrical connection from which module to which module is connected, and these connections are implemented through metal layers. So from which metal layer the connection will be drawn. Routing is all about that. So routing is divided into 3 major steps: global, detailed and specialized routing. The layout region is represented during global routing using a coarse grid of global routing cells, G cells, or more general routing regions, channels, switch boxes. After global routing, each net undergoes detailed routing. So first is global routing, and that uses a coarse grid, and detailed routing is more specific about layers, metal layers, via, and at which layer it will get connected and all, which pin will go to which layer. So that is much more, detailed routing is much more specific about routing flags, vias and metal layers. And the layout region is represented during global routing using a coarse grid of global routing cells or more general routing regions like channels and switch boxes. After global routing, each net undergoes detailed routing. And objective of detailed routing: assign route segments of signal nets to specific routing tracks, vias and metal layers while following global route and design rule. So global route uses coarse grid, and in detailed routing follows global routing and do more specific allocation of vias and metal layers and routing tracks, and it also follows design rule. And what are the key advantages? A detailed routing of one cell can be performed independently as long as routes remain connected across neighboring G cells. If the design is very big and complex, each G cell can be independently routed. The designer can concentrate on the smaller part, although the G cell must be connected to its neighboring G cells. And this enables an efficient divide and conquer strategy. This way small part is done, and that when the design is big and complex, that gives an edge. This approach gives an efficiency. So this enables an efficient divide and conquer strategy and supports parallel algorithm. If routing on multiple section of the design runs parallelly, actually it saves the time, allowing detailed routing runtime to theoretically scale linearly with layout size. So the runtime is linearly related with the layout size. If the layout size is big, then runtime is more. If the relationship would have been quadratic or exponential, then it would have been a little bit more complex. And traditionally, detailed routing occurs within routing regions such as channels and switch boxes. Modern designs use over the cell routing, allowing routing over standard cell. Over the cell or OTC routing, we will discuss in later slide in detail. In case of modern designs, OTC routing is used. Due to technology scaling, modern detailed router must consider manufacturing rules and impact of manufacturing faults. So manufacturing faults like reliability and variability impacts must be considered, and it must strictly follow the design rules, because in advanced node, the error related to the lithography is much more prominent. Detailed routing must follow all these rules very strictly. We are done with this slide. We will move to the next slide. Different routing techniques: channel routing, switchbox routing, OTC or over-the-cell routing, and classical channel routing. Type of detailed routing. The first one is channel routing. Type of detailed routing where connections between terminal pins are routed within a channel with no obstacle. This is channel routing. Connections between nets are done. This is the channel and there is no obstacle, and pins are on the opposite side. And the connections run from left to right, that is horizontally. Pins are located on opposite sides of the channel. Conventionally, the channel is oriented horizontally, this direction, with pins on top and bottom. In row-based layouts, routing channels typically have uniform width. In gate array and standard cell circuits with more than 3 metal layers, channel height or number of routing tracks is also uniform. Next is switchbox routing, used when pin locations are on all 4 sides of a fixed size routing region. So this is a fixed size routing region, and pin connections are on the 4 different sides, not on opposite top and bottom sides. So that is switchbox routing. There is a design, and these are 4 modules, how it's connected. If we want to route this area, pins are on opposite sides, here also like that. So this portion can be done by channel routing, and here in the between, when all the pin connection, all the nets are crossing each other in this zone is routed by switchbox routing. OTC or over the cell routing utilizes additional metal tracks, that is metal 3 and metal 4, that are not obstructed by cells, allows routes to cross over cells and channels. Only metal layers and tracks not occupied by cells can be used. When cells use only polysilicon and metal 1, routing can be performed on metal 2 and metal 3, etc., and unused metal 1 resources. So this is a channel routing situation, and this is the 3-layer OTC routing. We can see that number of connections are more here compared to this one, and here is over the cell, these connections is done over the standard cells, and here congestion is less, and metal 3 layer is used for this purpose. And classical channel routing area is rectangular grid with pin location on top and bottom boundaries. Pin are placed on vertical grid lines or columns. Channel height depends on number of tracks needed to route all nets. In 2-layer routing, 1 layer is reserved for horizontal track, while other layer is reserved for vertical track. Preferred routing direction is determined by floor plan and standard cell row orientation. That is classical channel routing. So these are routing techniques. We are done with this slide, and we will move to the next slide. Horizontal and vertical constraint. Horizontal constraint. A horizontal constraint between 2 nets occur when their horizontal segments overlap while being placed on same track. So we cannot place them on the same track. There is an example. This is A and this is B and this is C. So Look, C and B, they are crossing each other. If we place these two nets on the same track, they will overlap. Although if we place A and B on the same track, or A and C, they are not overlapping each other. So we can place A and C or A and B, they are horizontally unconstrained, whereas C and B are horizontally constrained. We cannot put them in the same track. That is horizontal constraint. Try to remember this. We will use this concept in later slide. And vertical constraint. Vertical constraint, a vertical constraint between two nets when they have pins in the same column. Look, A and B, they are on the same column. Here B and A are not in same column, although here A and B are in the same column. So this means that the vertical segment extending from top must stop within a short distance to avoid overlapping with the vertical segment coming from bottom in the same column. So that has stopped. If each net is assigned to a single horizontal track, the horizontal segment of a net from top must be placed above that of a net from bottom in the same column. In figure, that segment A is placed on B. In figure, this constraint ensures that net A's horizontal segment is placed above net B's. To resolve this constraint, at least 3 columns are needed to separate the two nets, while a vertical constraint implies a horizontal constraint. If this situation is quite similar like this, if that is vertically constrained, that is also horizontally constrained. Although the reverse is not always true. While a vertical constraint implies a horizontal constraint, the reverse is not always true. However, both constraints must be considered when assigning segments within a channel. If there is a pair of in both the column, it's vertically constrained. So in this case, we have to add another net. So we are done with this slide. We will move to the next slide. Now zone representation. Zone representation in a channel, each horizontal wire segment must extend at least from the leftmost to the rightmost pin of its net. Otherwise the connection is not complete. Each horizontal wire segment, the wire segment connecting to remote pins, they must be extend at least from the leftmost to the rightmost pin of its net. So let S column or set column represent the set of nets passing through column call. This includes net either have a pin in column or connect to pins on both sides of column. Since horizontal, this is a rule. Just remember, since horizontal segments cannot overlap, each net in S column must be assigned a separate track within that column. However, not all columns are necessary to define the entire channel. So rule is, so these are the pins, and now if we draw columns like this, so A, B, C, D, E, F, G, H, I, J, K. So we are only considering these 4 because other columns are subset of either of these 4. If we consider, the rule is pin assigned to that column is either it's starting from here or connecting the, if that is set A, then the rule is that set represent the set of nets passing through column. Either it has a pin in column or it connects pin on either side of the column. So here only one pin. In B, this net is connecting on 2 sides. So these from this one pin, this pin and that pin. Although if we consider the C, we have all these 3 and more 2. So this is a bigger set. SA and SB are subset of SC. So we will consider set C, not A and B. This way, these 4 are considered. If a column I has a net set SI that is a subset of another column J, that is SI belongs to SJ, then SI can be ignored as it imposes fewer constraints on routing. In the above figure, every S column is a subset of at least one of SC, SF, SG or SI. These columns C, F, G and I form minimal set needed as they collectively include all nets. The relative positions of net in channel routing instance defined by horizontal and vertical constraint can be represented using horizontal and vertical constraint graphs. These graphs help to estimate the minimum number of tracks needed and identify potential routing conflicts. In the next slide, we will see that how this zone representation can be expressed in terms of vertical and horizontal constraint graphs also. Now let's see what is happening here. This is connecting A to A, that is A, net A, that is net B, this is net C, this is net D, and this is net E. So A, this is B, this is C, this is D, this is E. So here under this column A, B, C, D and E. And now if we consider this column F, so here this one is connecting D. D is connected, pin F is there, pin F, pin A is there, pin F, pin A, and this D, this is net A and net F. So A and F, and these on two side D. So this is D, 3 nets. Now SG on G, G and F, and this is D on G, F and D, and on I, D and that is H. So G is here, H is here, and D is here, H is here, and this G and G connected, so G is here. So this way zone representation is done. So we are done with this slide. We will move to the next slide. Now let's see how from zone representation we can get horizontal and vertical constraint graph. Now horizontal constraint graph, a graphical representation can be used to depict the nets within a channel. Graph theory, it's a mathematical theory from abstract algebra, and that is extensively used in this placement, routing, in all these steps. So this can be done using a horizontal constraint graph. A graphical representation can be used to depict the nets within a channel. Vertical and horizontal constraint graph we have already used in our previous episodes on physical design, and in all these episodes we can see this graph theory from abstract algebra that is absolutely very necessary and extensively used in physical design. Placement, routing, in all these steps, and all the tools, the EDA tools which does it, they all have these mathematical models inside it. So this can be done using a horizontal constraint graph or HCG when nodes, that is V, represent the nets in the netlist, and edges exist between two nodes if their corresponding nets belong to the same set. Here in the same set, this set is A, B, C, D, E. Now let's see A, B, C, D and E. Look, A is connected to D, B, E, C. This way B is connected to A, C, D, E. C is connected to all other 4, A, B, D, E. E is connected to D, A, B, C, and D is connected to A, B, E, C. In graph, these are nodes and this is edge. Nodes here represent the net between these two nodes, and edge is present if they belong to the same column. Since these A, B, C, D, E are all these 5 nodes belong, nets or nodes belong to this column, so they are interconnected. Each of them are connected to rest of 4. Now SF or set F. Set F is A, F and D. A, F and D. D is connected to F and A is connected to F and D. F is connected to A and D. That is also done. Now SG is G, F and D. Now G, F and D. This set also, they are interconnected. Each of them is connected to other 2. And similarly for I, G, H and D. G, H and D. Here also, each of 3 are connected with other 2. So figure 4 shows the HCG for channel routing example in figure 3. We have repeated the figure 3 here just for reference, and the minimum number of tracks required for channel routing can be determined using either the HCG or zone representation. This minimum is given by largest S column set. So minimal columns, and we have taken only those, and this is the HCG or horizontal constraint graph of this set, of this zone representation. Now vertical constraint graph. Vertical constraint graph or VCG represents vertical constraints in channel routing. Nodes V represents nets, directed edges. E exists between nodes if one net must be placed above another. In figure 5, some edges like B to C are omitted if they can be inferred from other edges like B to E and E to C. So here we can see that in VCG or vertical constraint graph, nodes represent nets. There is directed edges exist between nodes if one net must be placed above another, like B to E. So net B is placed above net E, and net D is placed above net B, and E is placed above C, and G is placed above F, and F is placed above A, and H is separate. And here another scenario, a cycle in VCG indicates a conflict where two nets overlap in column. So with this horizontal and vertical graph, we can easily determine that which net are connected, which net. And here in vertical constraint graph, we can determine which net must be placed above which net must be placed above and which will remain below of that. The scenario is completely clear from these two graphs. This diagram is different. A cycle in VCG indicates a conflict where two nets overlap in a column, both two nets, meaning their horizontal segments would need to be both above and below each other, an impossible situation. This is resolved by splitting the net and adding an extra track like A to A and B to B, and that this way that is splitted and issue is resolved. We are done with this slide. We will move to the next slide. Now channel routing with left edge algorithm. Channel routing algorithms. Channel routing aims to minimize the number of tracks needed for routing. In gate array design, where channel height is usually fixed, algorithms are developed to ensure complete or 100% routing. Left edge algorithm, an early channel routing algorithm, was developed by Hashimoto and Stevens. Their simple and widely used left edge heuristic based on VCG and zone representation efficiently maximizes track usage. The VCG determines the order in which nets are assigned to tracks, while the zone representation decides which net can share the same track. Each net uses only one horizontal segment or trunk. Obviously, we know at which order, like here, since it directed, A must be placed over E, A and D must be placed over E, and C must be placed below E net E, and similarly D and J must be placed above I, whereas I must be placed above H, and again J must be placed above G, F and B, and here B is at the lowest level, then above it F and above it G. This way, the routing, that is a vertical constraint graph. That information we can get from this vertical constraint graph, and it actually uses VCG and zone representation. The left edge algorithm work as follows. Start with topmost track. For all unassigned nets, generate the VCG and zone representation. Process nets from left to right, assigning each to the current track if it has no predecessor in the VCG or it does not conflict with previously assigned net. Once a net is assigned, remove it from the unassigned list, move to the next track and repeat the process until all nets are assigned. So one at a time we are taking. Start with the topmost track. So first track A, first track, for all unassigned nets, generate the VCG and zone representation. For all other unused nets, it's using the VCG, it's creating the VCG and zone representation. Process nets from left to right. From left to right, start processing nets. For all unassigned nets, generate the VCG. Now we have started with topmost track. So process nets from left to right and assign each of their current track. Now first A is assigned, and then it has no predecessor in the VCG. If that has no predecessor, if it has no predecessor, it's a starting point. So we will start with that. We will assign it, and it does not conflict with previously assigned net. So it's the starting point A, and once the net is assigned, remove it from unassigned. It's assigned, so we are removing it from the unassigned list. Now next, with the rest of the unassigned pin, we are again doing the VCG and we will move to the next track. This way we will keep doing this. Move the next track and repeat the process until all nets are assigned. This algorithm finds a solution with the minimum number of tracks if the VCG has no cycles. Yoshimura later improved track selection by considering net length in the VCG, and Yoshimura and Co. further optimized track usage by splitting nets before constructing the VCG. That was a modification by Yoshimura and Co. So this way, this is the most early channel routing algorithm, that is left edge algorithm. So we are done with that and we will move to the next slide. To handle cycles in VCG, an L-shaped dogleg, this L-shaped dogleg can be used. Doglegs help resolve conflicts in VCG and reduce the total number of tracks. Dogleg algorithm developed in 1970s eliminates cycles and minimizes routing tracks by extending the left edge algorithm. It splits P pin nets P greater than 2 into P minus 1 horizontal segments, but only in columns where the net has a pin, assuming no extra vertical tracks are available. After splitting, the algorithm follows a left edge approach with subnets represented in VCG and zone representation. So dogleg routing also use, in a part of it, also use left edge algorithm. Before that, it splits the net. Dogleg algorithm that is developed in 1970s eliminates cycles and minimizes routing tracks by extending left edge algorithm. It's an extension. It splits P pin nets P greater than 2 into P minus 1 horizontal segment, but only in columns where the net has a pin, assuming no extra vertical tracks are available. Channel routing, this is a channel routing problem. Like it's a vertically constrained from A to B is just opposite vertically coming from lower column. So it's a vertically constrained situation, channel routing issue. And now VCG without net splitting, like C is at the bottom, net B must be above it and net A must be above it, this way. Now channel routing solution is like that. A is connected. Now B must be connected like this and C like that. And now look how many tracks are used. And now net splitting, it's splitting the net B, it splits P pin nets when P is greater than 2 into P minus 1 horizontal segments. Like here, B net are P greater than 2, 3. 3 nets of B are represent. So 3 is greater than 2 and 3 P minus 1, 3 minus 1, that is 2. It will split the net into 2 horizontal segment. So it has splitted like this way, B1 and B2. These two. A is connected like that, C is connected like that, and in case of B, it's B1B is connected to through B1 and this split, and now it's a little bit vertically shifted. And this, look, this one compared to this one is much more clearer. Channel routing solution. Now VCG without net splitting, that should be with net splitting. So A to B1 must be below A and B2 must be above C. So it's splitted like that only. So A to, it was directly A to B and C, and here it's like A to B1 and now B1 to C. This B is splitted into 2. So these 3 nets are connected like that. So that is channel routing solution by dogleg routing. And here is the dogleg, this structure. So this is dogleg algorithm. We are done with this slide. We will move to the next slide. Now switchbox routing. Switchbox routing algorithms are often derived from channel routing techniques. Look extended a greedy channel router by Rivest and Fiducia to develop a switchbox routing algorithm with key improvements like pin assignments are made on all 4 sides. A horizontal track is assigned automatically to a pin on the left. Jogs are used for top and bottom pins for horizontal tracks connected to the rightmost pin. And while this algorithm performs similarly to the greedy channel router, it does not guarantee full routability due to fixed switchbox dimension. Switchbox dimension is fixed. Austerhoff et al. Introduced a channel and switchbox router that consider obstacles like pre-routed nets. Kohun and Heck developed Beaver, which optimizes routing area and via usage. And Beaver offers flexibility in layer routing and employs 4 strategies: corner routing, line sweep routing, thread routing, and layer assignment. Switchbox routing has gone through a many improvisation. So Beaver offers flexibility in layer routing and employs 4 strategies: corner routing, line sweep routing, thread routing, and layer assignments. Corner routing uses horizontal and vertical segments forming bends. Line sweep routing handles simple connections and straight segments. Thread routing supports various connection types, and layer assignment optimizes layer usage. All 4 sides, here it's mentioned pins like 0, D, F, H, E, C, C, and here 0, G, F. So this connection is a little bit more complicated, and we have seen in one of our previous slide that switchbox is done where from different modules or different components the connections are coming and they are meeting a place. This zone where pin connections are coming from all sides, this complicated portion that is routed by switchbox routing. So look, D is like this, routed like this. G is a little bit complex here. G is like that. F is like that. So top, bottom, left and right. Pin connections are mentioned. This is the initial and this is the final scenario, how it should connect it. Corner routing uses horizontal and vertical segments forming bends. In this corner routing, these bends are here. Line sweep routing handles simple connection and straight segments. That is done by line sweep routing. Thread routing supports various connections types. It's a multi-type connections are connected by this thread routing. And layer assignment optimizes layer usage. How many layers should be used? That is using 4 different strategies do the routing, and that offers a flexibility. Now, Beaver surpasses previous academic routers in routing area and via efficiency. Another notable switchbox router, Packer, developed by Geres and Herman in 1989, follows 3 main steps: routing each net independently without considering capacity constraint, and resolving conflict using connectivity, preserving local transformation, and modifying net segments locally to reduce congestion. Packer was developed by Geres and Herman in 1989, and that has 3 main steps, like routing each net independently without considering any other capacity constraint, and resolving conflict using connectivity, preserving local transformation, and modifying net segments locally to reduce the congestion. And Beaver is much more better than that for switchbox routing. In case of switchbox routing, Beaver performs better and much more flexible also. So these are all academic routers done in purpose of academic usage. So we are done with this slide and we will move to the next slide. Over the cell routing algorithms. Most routing algorithms focus on 2-layer routing. However, modern standard cell designs use multiple layers, requiring extensions to this algorithm. One common approach places cells back to back or without routing channels. Internal routing primarily use poly and metal 1. So above poly layer, there is metal 1 layer, then metal 2, metal 3. While higher metal layers like metal 2 and metal 3 remain unobstructed and are used for over-the-cell routing. These layers are represented by coarse routing grid of G-cell. Nets are first globally routed as Steiner trees and then detail routed. Mostly internal routing primarily uses the poly and metal layers, so metal 2 and metal 3 layers. These are unobstructed and that is used in OTC. Nets are first globally routed as Steiner trees and then detail routed. Another approach introduces channels between cells, but routing within them is limited to internal layers like poly and metal 1. Higher metal layers, metal 2 and metal 3, handle most routing, making traditional routing channels unnecessary. Instead, routing occurs across the entire chip rather than in defined channels or switchbacks. OTC routing often coexists with channel routing. For example, IP block may block routing on lower metal layers, forming channels or switch boxes between them. FPGA fabrics use fewer metal layers to reduce cost. Clustering interconnects into channels. FPGA also include pre-designed components like multipliers and DSP block that rely on OTC routing. Modern FPGA feature express wires on higher metal layer that cross logic elements. So OTC routing that exists with channel routing also, and in poly and metal 1, these layers are mostly used, and above layers metal 2, metal 3 are unobstructed. So OTC actually use those metal layers. This is over the cell or OTC routing algorithm. We are done with this slide. We will move to the next slide. OTC routing methodology. OTC routing follow 3 steps. Select nets to be routed outside the channel. Route these nets in the OTC area. Route the remaining nets within the channel. Several advanced OTC routing algorithms have been developed. Chameleon OTC router by Brown et al. Generates net topologies using 2 or 3 metal layers to minimize routing area. Assigns net segment to tracks. Consider technology parameter per layer such as wire width and spacing. Pong, Wong and Liu's approach, that's another approach, initially routes all nets in 2 layers, then map them onto 3 layers, uses shortest path and planar routing algorithm to minimize wearing area, assumes HVH model, that is horizontal track in layer 1 and 3, vertical track in layer 2 can be extended to 4 layer routing. That's another approach. Ho et al.'s heuristic based method, that is greedy approach with iterative heuristics, successfully solved difficult example using 19 track on 2 layers matching the optimal zone representation. And Weiser by Holmes, Sherwani and Saravzadeh uses free pin positions and cell areas to increase OTC routing capacity, selects net strategically for OTC routing. So these are 4 approaches. Now these are the OTC over the cell connections and these feed-through passes are present. We have mentioned that in global routing in standard cell for standard cell design, these are feed-through passes. Number of pins are increasing, number of connections are more than using OTC. We can make this channel uncongested. So that is methodology of OTC routing, and we are done with this slide. We will move to the next slide. Modern challenges in detailed routing. Technology scaling and wear widths. Demand for low cost, high performance and low power ICs has driven technology scaling since the 1960s. Different metal layers use wear and varying widths, with wider wears on higher layers, improving signal speed but reducing routing tracks. Thicker wears are commonly used for clock, power supply and global interconnect. Now, routing complexity and layer configuration. Modern ICs use different metal layers configuration to optimize performance via connecting wears of different with block routing resources on layers with smaller pitches. Since wider wears are on higher layers used, that improves actually signal speed, although track for routing that is reduced, and thicker wires are used for clock, power supply and global interconnects. Now, manufacturing yield and detailed routing. Yield concerns require VR doubling and non-tree routing for redundancy. At advanced node, design rule become restrictive and specifying minimum spacing between wires and vias based on width and corner proximity. Forbidden pitch rules prohibit certain wire spacing while allowing others. So the conditions become more stringent. And via defects and mitigation. Vias connect wires between metal layers but may misalign or degrade due to electromigration. Partial via failure increases resistance, leading to timing violation. Complete failure disconnects nets. Double vias improve reliability but require additional area and adherence to design rules. Congested areas may limit via doubling options. So there are solutions, although since space is concerned, that thing can be limited by area also. Available area. Now, interconnect defects and redundancy measures. Shorts and open, that could be a possibility. Shorts or unintended wear connections are mitigated by increased spacing. These are interconnect defects that can happen during fabrication. In some other episode, we will discuss about these shorts and open things. These are very common errors come while fabrication, and this could be reason of IC failure. Shorts are mitigated by increasing spacing, though in excessive spacing raises wear length. Open are addressed via non-tree routing and redundant wiring, which improves reliability but increases short risk. So there are pros and cons we have to balance and optimize. Antenna-induced defect. Excessive charge buildup during plasma etching can damage transistor gates. Mitigation involves controlling metal to gate area ratios and rerouting via new or relocated vias. Manufacturability, aware routing, yield optimized detailed routing is proposed, but its benefits are hard to quantify pre-manufacturing, limiting industry adoption. So there are so many challenges already present, and since the device dimension reducing and because of excessive scaling and small dimension of devices and allied fabrication related reliability issues, the detailed routing become more complex and tough to achieve good result. We are done with this slide, and now this is an example. So in 130 nanometer, look how many layers are there. M1, M2, M3, M4, M5, M6. Now 90 nanometer, number of layers increasing, number of in 65 nanometer more, 45 nanometer more, and 32 nanometer. So layer stacks are shown. So number of layers are increasing as the scaling has been done from 130 nanometer to 32 nanometer. Number of layers increasing. As an example, it has been shown here. So we are done with this slide, and we are done with our today's discussion. So that is all we had about detailed routing. Here we have discussed different aspects of detailed routing. After global routing, the next step is detailed routing. We have completed it today. Now let's take a look at the pointers we are going to discuss in today's episode. First, design flow and specialized routing. This is the third episode in routing in physical design, and we have already covered global and detailed routing. Now it's time for specialized routing. Next, area routing, key objectives and optimization factors. Next, basic concept in clock networks. After that, delay in clock networks, clock skew and clock routing problems, modern clock tree synthesis techniques. This is the first slide on this topic. Next, another slide on modern clock tree synthesis techniques. And then MMM versus RGM. These are two methods. There is a comparison between them. Then modern clock tree synthesis techniques. This is the third slide on the topic, and clock skew optimization and power trade-off first slide, and clock tree optimization and power trade-off second slide. So these are the pointers we will discuss in our today's episode. We are done with this slide. Now let's move to the next slide. Design flow and specialized routing. This diagram we are using for last few episodes, and today also we will take reference of this one. Once the flow enters physical design, there are multiple steps like partitioning, chip planning, placement, clock tree synthesis, signal routing, and finally timing closure. So in signal routing, we have already covered global routing and detailed routing, and today it's time for specialized routing. In digital integrated circuit, first signal wires undergo global routing and then followed by detailed routing. We all know that. However, in certain designs such as analog circuits and printed circuit boards, that is PCBs, with gridless routing or trackless routing, this distinction is unnecessary. It doesn't need this. Similarly, older or smaller designs with one or two metal layers also fall into this category. For this type of routing, we take specialized routing. Now, when global and detailed routing are not handled separately, area routing is used to directly establish metal connections for signal routing. Unlike routing with multiple metal layers, area routing prioritizes minimizing wire crossing. Clock signals require special consideration. This is the basic about specialized routing. We are done with this slide, and now let's move to the next slide. Area routing, key objective and optimization factor. We have already mentioned about area routing. When there is a discrimination between global and detailed routing is not required. Overall, it's done by area routing. Objective, area routing aims to connect all net while bypassing global routing, operating within the available layout pace, adhering to geometric and electrical constraints. So that is global routing. Minimize total routed length and number of vias, optimizing wear area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. So these are optimization goal. Minimize total routed length and number of vias, optimize wearing area and routing layer use, reduce circuit delay with maintaining uniform wear density, lower capacitive coupling between adjacent routes. Now, constraint considered. Technological constraint like number of technological constraints like number of routing layers, wherewith electrical constraint like signal integrity, coupling effects, geometric constraints like preferred routing direction, wear pitch, etc. So these are the constraints. What are in number of routing layers, wherewith these are technological constraint. Now, electrical constraint like signal integrity, coupling effects, and geometrical constraint like preferred routing direction, wear pitch. Three types of technological constraint, electrical constraint, and geometric constraint. Now, impact of net ordering. The sequence of net routing affects efficiency and runtime. Greedy wear length based routing can cause inefficiencies, and multi-pin net require careful decomposition and ordering. That is impact of net ordering. In which sequence net ordering is done that affect the efficiency and runtime, and greedy wear length based routing can cause inefficiencies. So now net and pin ordering strategies. Pin ordering use Steiner tree based algorithm to convert multi-pin nets into two-pin nets, sort pin locations by x coordinate, and connect from left to right using shortest path algorithm. And net ordering challenges. Finding optimal net order is complex. N factorial possibilities are there. Now, net ordering rules are there. Nets with larger aspect ratios are routed first. If aspect ratio is the same, the shorter net length is prioritized. If a net's pins are fully inside another net's bounding box, it is routed first. The net with fewer interfering pins in its bounding box is routed first. Ties are resolved based on total pin count inside the bounding box. These are the rules followed. So this diagram is showing there are two ways to connect this net. There are two ways. It can be routed this way, can be routed this way also. Now there are 4 nodes and 2 two nets are mentioned, like A and A. These net can be connected this way, these two, and these can also be connected this way. It's shown two different ways of connection in both the diagrams. So we are done with this slide. We will move to the next slide. Basic concepts in clock networks. Most digital designs are synchronous, that is, computations occur in sync with the clock signal. The clock ensures that internal state variables and inputs are processed correctly through combinational logic, generating new outputs and state updates. The clock signal, often called the system's heartbeat, can be generated off-chip or by on-chip analog circuits like PLL and DLL. Its frequency may be divided or multiplied depending on the need of the different circuit blocks. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all parts of the circuit receive the clock simultaneously. So this is the main focus in case of clock tree. Clock tree routing is used to distribute the clock signal efficiently. It builds a clock tree for each clock domain, ensuring that the signal reaches all flip-flops and latches at the same time. Unlike other routing types, clock routing focuses on minimizing skew so that all part of the circuit receive the clock simultaneously. Now, a clock routing problem involves connecting n+1 terminals. A clock routing solution consists of wire segments that connect all terminals, ensuring the signal from the source reaches every sink. This solution has two key aspects: topology and embedding. So clock routing problem involves connecting n+1 terminal, and clock routing solution consists of wire segments that connect all the terminals, ensuring that signal from source reaches every sink. This solution has two key aspects. One is topology and other one is embedding. Clock tree topology are rooted binary tree G with n leaves representing the sink's internal node include the source and any additional Steiner points, and embedding defines the exact physical placement of edges and internal nodes in the topology. Figure A illustrates a 6-sink clock tree instance. This is a 6-sink clock tree. There are 6 sinks, and figure B shows its connection topology. So connection topology, it's a rooted binary tree with n leaves. So S1, S2, S3, S4. There are n number of sinks, so n number of leaves. This is the clock tree topology. And embedding, figure C presents a possible embedded clock tree solution. It's a possible embedded clock tree like S0. From there, this connection is going like that. S0 to S1 and S2, that is U1, this one. Now U2, U3, U4. From S0, it's coming to U2. From there, U3 and U4. And from U4, S5 and S6. And U3, S3 and S4. So this is the embedded clock tree solution, and this is the clock tree topology. We are done with this slide. We will move to the next slide. Delay in clock networks. Signal delay is the time a signal takes to switch states, that is low to high or high to low, as it travels through a routing tree. It starts at logic gate outputs built from nonlinear transistor and moves through wires and vias, which add parasitic effects. We all know about parasitic effects of wires. In our interconnect series, we have discussed that parasitic effect in detail. Now, exact delay calculations are complex, so tools like SPICE or prime time are used for precise sign of delay measurement. However, place and route algorithms use approximate models such as linear and Elmore delay models. Linear delay model. In the linear delay model, signal delay between nodes I and J is proportional to the path length in the routing tree, independent of connection topology. The normalized linear delay between nodes U and W is sum of edge lengths along the path. On-chip wires have both resistance and capacitance, which increase with length due to RC effects, where delay grows quadratically, which the linear model does not capture. Despite this, it remains useful in design tools, especially for older technologies with lower drive resistance and wider wires. Its simplicity makes it widely used in EDA software. Linear delay model, although it's a linear model, and when RC comes into play, the wire delay increases or grows quadratically. It's a quadratically increasing, and we are trying to model it through linear delay model. It's not appropriate, although it's a good assumption because it's a simple model and it's very useful for older technologies with lower drive resistance. delays. And Elmore delay model, the Elmore delay model we have already discussed in interconnect series in the delay episode. The Elmore delay model provides a more accurate delay estimate by considering resistances and capacitances in the routing tree, especially for modern circuits with significant RC effect. Physical design tools use Elmore delay approximation for three key reasons. First, it considers the effect of off-path wire capacitance on sync delay. Second, it provides a good balance of accuracy and correlation with circuit simulator estimates. And third, it can be computed efficiently in linear time using two depth-first traversals, one to determine capacitance below each node and another to calculate delays from the source to each node. It's considered downstream and it's upstream. These are the leaf like a tree. Current flow from this direction to that direction and the current out this way. The calculation is done. We have already discussed in detail in our interconnect series. Link is provided in the description. You can take a look if you want the reference of Elmore delay model. Delay in clock network is basically calculated by linear delay model, which works quite efficiently for older nodes, and Elmore delay model is much more accurate approximation. We are done with this slide. We will move to the next slide. Clock skew. There is one episode, different delay types in VLSI. There also we have discussed about clock skew. Clock skew is a maximum difference in clock signal arrival times between sinks. So clock skew and clock routing problems. We have already discussed about clock skew in one episode called different types of delays in VLSI. Link of that episode is provided in the description. You can take reference of that episode also, although the perspective a little bit different there. Clock skew. This is maximum difference in clock signal arrival times between sinks. Since the clock signal should reach all sinks simultaneously, minimizing skew is crucial for circuit timing. Ideally, clock should reach every sink at the same time, although it doesn't happen because the signal takes finite time to travel through the wires. Local skew. The maximum difference in clock arrival times between related sinks that are sequentially adjacent, meaning there is a combinational logic path between them. Usually there is a clock, there is a sequential block, and then some combinational blocks are there, so it takes some time to travel. So local skew is the maximum difference in clock arrival times between related sinks, that is sinks that are sequentially adjacent, meaning there is a combinational logic part between them, that is local skew. And now global skew, the maximum difference in clock arrival times between any two sinks, whether related or not. It is difference between the shortest and longest source to sink path delays in the clock tree. In most cases, global skew is what is referred to as clock skew in design analysis. So that is a maximum. If that is the clock and there is the closest sink present is there and the farthest is here, the skew from these two, the time difference in reaching this sink and that sink would be different, and that is the maximum difference when it's reaching the shortest path, covering the shortest path and the longest source to sink path. Difference between these two delays in the clock tree, that is actually referred as clock skew in design analysis. That is the maximum clock skew, and that is global clock skew mentioned at clock skew. There are few clock routing problems, like modern low power clock network design integrates zero skew trees and relies on SPICE for accurate circuit simulation. Zero skew tree ZST problem. A ZST ensures that the clock signal reaches all sink at the same time. That is zero skew. No skew is there. Skew is defined using a delay estimate like linear or Elmore delay. Bounded skew tree or BST problem. While ZST are useful in theory, exact zero skew is not practical due to increased wire length leading to higher capacitance and manufacturing variance, which cause difference in wire resistance and capacitance. Instead, real world clock tree allowed a small skew within a given bound. So ideally zero skew is not possible. So a small skew within a given bound, that is bounded skew tree, is acceptable level. A skew with an acceptable level is approved or allowed. Now useful skew tree problem. In some cases global skew control is unnecessary. Instead the focus is on local skew between related flip-flops or latches. Enforcing strict global skew constraint can overcomplicate the problem. So in some cases it's not necessary. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signals between flip-flops arrive neither too late nor too early. Double clocking. By optimizing sink arrival times, the clock period P can be reduced, improving circuit performance. Fishburne proposed a useful skew method where clock arrival times at sinks are intentionally adjusted to minimize the clock period, maximize the timing margin. This approach helps ensure that data signals between flip-flop arrive neither too late, that is zero clocking, or not too early, double clocking. By optimizing sync arrival times, the clock period T can be reduced, improving circuit performance. There are two diagrams, that is minimal clock period time 0 nanosecond at 0 nanosecond, and after 2 nanosecond it's reaching here. After 6 nanosecond is reaching FF3, third flip-flop. So minimum clock period T equal to 6 nanosecond with 0 skew. And here skew is a little bit adjusted, like there is a skew of 2 nanosecond and it's reaching, and this one has 2 nanosecond skew. So if between these FF1 and FF2 there is a skew happens because of a combinational logic path is there, and for this path if the signal takes 2 nanosecond, so here when it's reaching FF2 it's basically 0 skew, and when it's reaching here in 6 nanosecond, so it's effectively becoming 4 nanosecond with 2 nanosecond skew. So minimum clock period becoming 4 nanosecond with 2 nanosecond skew. So we are done with this slide. We will move to the next slide. So now modern clock tree synthesis. This is the first slide on this topic. So clock trees are crucial in synchronous circuit design. Obviously everything needs clock signals. There have to be a clock tree and affecting both performance and power consumption. And a well-designed clock tree ensures low skew, delivering the clock signal to all sequential gates simultaneously. That's the requirement or the expectation from a well-designed clock tree. And after the initial tree construction, the clock tree goes through clock buffer insertion to strengthen the signal and skew optimization to further reduce timing variation. So that is the basic. Constructing tree with zero global skew. 5 early clock tree construction algorithms whose core ideas still influence modern EDA tools. These algorithms address different scenarios like builds a clock tree without considering exact sync positions, construct both the tree structure and physical layout simultaneously, and tree is given a predefined topology determines its physical placement. So H-tree, the H-tree is a self-similar fractal structure that ensures exact zero skew due to its symmetry. It's built by recursively dividing a unit square. A central segment is placed through the root. Two shorter perpendicular segments extend to the centers of 4 quadrants. This process continues until reaching all sinks. The H-tree is widely used for top-level clock distribution, but it has limitations like blockages can disrupt the pattern, irregular sync placement makes direct implementation difficult, and high routing cost. To reduce signal inflection, where tapering is used, where the width halves at each branching point. This is H-tree. H-tree has a symmetrical structure, although it has some cons, some downside. That's why where tapering is used, where width halves at each branching point. This is H-tree. We are done with this slide. We will move to the next slide. Modern clock tree synthesis. This is the second slide. Method of means and medians. The MMM algorithm proposed by Jackson, Srinivasan and Pu in 1990 improves on the H-tree by handling arbitrarily placed sinks. It follows a recursive approach like partition terminals into 2 equal subsets based on median. It's partitioning. Again, it's based on median. So these medians are connected. Again, based on this median, it's divided in this way and this way and this way based on median. So many small rectangular blocks are there. This method is flexible and adapts to different sync distribution. While MMM can be simplified into an H-tree like approach, it only minimizes skew heuristically. In the worst case, the longest source to sync path can be as large as the chip diameter, making the algorithm's effectiveness highly dependent on cut direction selection. And this is improvisation over H-tree. Although it has a downside like effectiveness of the algorithm depends on the cut direction selection. Now recursive geometric matching or RGM. The RGM algorithm introduced in 1991 is a bottom-up approach to clock tree construction unlike the top-down MMM algorithm. How RGM works, the algorithm finds a minimum cost geometric matching of n/2 line segment, ensuring no 2 segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew between connected sinks. The n/2 tapping points from one stage serve as input for the next matching step. The process continues until the clock tree is fully constructed. So here, clock tree structure started from median, here opposite. Any two adjacent sinks. So here algorithm is little bit different, like the algorithm finds a minimum cost geometric matching of n by 2 line segments, ensuring no two segments share an endpoint, no two segments share an endpoint while minimizing total segment length. After matching, a balance or tapping point is placed on each segment to maintain zero skew. So these 2 points are connected by this segment and these two segments are considered and they are connected. And in between there is a tapping point is found. These two segments are connected and there is a tapping point. So those tapping points, tapping point from one, there is a tapping point of these two, there is a tapping point of these two are connected. Now in these two between there is a tapping point and again tapping point from here. So these are connected like this, these are connected. Again these two are connected by this tapping point, these two sinks are connected by this tapping point, and these two tapping point are connected by another tapping point. This is the tapping point of these four final at this stage, and here these two, there is a tapping point, these two, there is a tapping point, and between these two tapping point there is another tapping point, and these tapping points are connected, and in between we find another tapping point and this tapping point, and here it means here meets here in another tapping point. It's a bottom-up approach and here it's top-down approach. So we are done with this slide and we will move to the next slide. Now let's take a look at the comparison of MMM and RGM. These four sinks and top-down approach, median is found here. Again, two medians are found this way. And here it's a connected segment and tapping point, and these two, this tapping point and this tapping point connected, and this is the tapping point. So RGM improves clock tree balance and reduces wire length. So we can easily see wire length is reduced here compared to MMM. Above figure compares MMM and RGM for 4 sinks. If MMM selects a poor cut direction, RGM can cut wire length in half. However, like MMM, RGM does not ensure zero skew. If two subtrees have very different delays and their roots are matched, finding a zero skew tapping point may not be possible. This is the comparison between MMM and RGM. We are done with this slide. We will move to the modern clock tree synthesis. This is the third slide on the same topic. Exact zero skew algorithm and deferred merge embedding. These two algorithms. Proposed in 1991, the exact zero skew algorithm improves upon RGM by ensuring precise skew balancing using Elmore delay model instead of the simpler linear model. It uses Elmore delay model. Key feature, it calculates exact zero skew tapping point using the Elmore delay model, leading to lower actual clock skew in real designs. When merging two subtrees with different sourcing delays, it adjusts wire length to equalize the delays. During merging, the zero skew tapping point is carefully placed along the matched segment. It equalizes the delay by adjusting the wire lengths. When two subtrees with different sourcing delays are merged, the algorithm adjusts wire lengths to equalize the delay, because when clock signal travels through wire, some delay also added there. During merging, the zero skew tapping point is carefully placed along the matched segment. So these two are subtrees and this is the tapping point. So this length is calculated accordingly to balance the skew. And another method is deferred merge embedding. The DME algorithm improves clock tree construction by delaying the selection of merging or tapping points for subtrees. Unlike earlier method that fixed internal node locations early, DME optimally places these nodes later, ensuring minimal source to sink delay and minimal total tree cost. So how DME works, unlike MMM and RGM, which only require a set of sink location, DME needs a predefined tree topology as input. Key advantage, MMM, RGM exact zero skew fix internal node positions too early, limiting flexibility, whereas DME ensures more optimal placement of internal nodes, leading to better clock tree performance. Deferred merge embedding and improvisation over the previous algorithms. So we are done with this slide. We will move to the next slide. Clock skew optimization and power trade-off. This is the first slide. Key challenges. Low clock skew is critical for high performance design. Clock networks consume significant power, requiring trade-offs between skew and capacitance. Accurate timing analysis is needed. All the simulations are time-consuming. Closed form delay models are inaccurate. A common approach is to optimize using Elmore delay model and then fine-tune with more accurate models. Now, clock tree optimization steps. There are multiple steps in that. First is geometric clock tree construction. initial clock buffer insertion, clock buffer sizing, wear sizing, and wear snaking. So these steps account for process, voltage, and temperature variations. Now, high-level skew optimization. Earlier, a single buffer was enough to drive the clock tree. Now, technology scaling, multiple buffers are required. Buffer insertion ensures that clock signal reaches all sync efficiently. And Ginneken's algorithm optimally buffers a tree to minimize Elmore delay that runs in n squared time, quadratic relation, and where n is number of buffer locations. And a faster O(n log n) variant improves scalability, optimizations reduce skew, power consumption, and variability effect. So, skew optimization is very important. Now, clock buffer sizing. Initial buffer sizes impact later optimizations. Best size is determined experimentally, that is binary search. To fix skew between two sinks S1 and S2, identify the unique path between them. Upsize buffers based on pre-computed tables, and larger buffers improve robustness but increase power and delay. That is about clock buffer sizing. So now clock skew optimization and power trade-off. This is the second slide. This is a diagram. We have already used it in variability episode. So here process level, device level, circuit level, and chip level variability factors are mentioned. So wear sizing, wear width affects power and manufacturing variation. Wider wears are more resilient to variation, although the capacitance and power consumption both are higher. Thinner wears are used in low power designs where width can be adjusted dynamically based on timing analysis. Now, low level skew optimization focuses on local adjustment with higher precision. Techniques wear sizing, that is adjust width for fine-tuned timing. Wear snaking, that is increase path length through delay fast signals. Wear detouring increases capacitance and resistance, so that slows down the propagation. Now, variation modeling. Process variation impact each transistor differently. Environmental factors, that is temperature, voltage fluctuation, affect performance. Now, two modeling approaches are there for Monte Carlo simulation, that is accurate but slow, and pre-computed lookup table, efficient and reusable. Captures worst case skew variation based on technology node, bufferware library, and path length, variation model, yield, etc. That enables fast, accurate optimizations, that is buffer sizing. And what are advanced clocking techniques? Active de-skewing and clock meshes, that is common in CPUs, and clock gating reduces power dissipation. These are advanced clocking techniques. We already have an episode on clock gating. Link is mentioned in the description. You can take reference if required. That is about specialized routing and clock tree routing. We are done with this slide and we are done with our today's episode. Thank you for watching up to this point. Don't forget to like, share and subscribe. In case you have any dislike, please put it as a comment. If you have a question or query, also put it as a comment. Thank you again and bye for today.